Yeah, for us it's the same. So it's good. Absolutely.
Mm-hmm.
Thailand will open country 1st November in some area.
Yeah, things are improving. I mean, we are pretty much back to normal. So the cases in my city are around 10 per day. So I mean, yeah, less than 100 per week, which is reasonable. So and cases are subsiding. So we hope to be back to the new normality in a few months, perhaps after Christmas. Early next year.
How about vaccination in Spain? Vaccination.
We are all pretty much all vaccinated. So the population has already received what they call the large immunity. So more than 70%. I think we're close to 85% already. So they're starting to vaccinate children now. So these are the only group that is left. So yeah, children already vaccinated from I think 15 to 19 years old, and teenagers below. I think this is the one that is left from 14, 15 below. So I mean, it will take just a few months. I think by Christmas everybody will be vaccinated, so we will be hopefully back to normal.
Professor Pasert have lunch now. he will come soon. He will come to job soon.
No problem. It's your lunchtime, so you really need a break. I'm sure that it was an exciting and busy morning.
I just finished my class also.
Oh, okay, I see. For me, it's really difficult to catch up with conferences and stuff these days. I mean, I have been delivering invited talks, keynotes, plenaries, but it's almost impossible to stay more than a couple of talks or 3 talks. There is always something in the pipeline. There is always a pending meeting. So it's really difficult to manage these events for an extended time. I hope that we can go back to normal. So because in presently is very different. So you meet people around and you are in the place focused on the conference. And at the same time, you can be doing something on the computer, but it's different. In here, there is always something going on.
One Thai student stay in your lab, right?
Yeah.
I see her Facebook. She really enjoys.
Yeah. So Jane has been here since March, I think. Yeah, she's here already for 7 months, 8 months. So she's enjoying. She's definitely having fun. But she's also been productive. So I'm happy that she's also generating some good results. She will have her first publication very soon. So it's going well.
Sorry, I asked Rafa about Alina. She stay with young researcher.
Yes. She's sleeping with the young researchers. But you may get to see Eva.
Very active researcher.
I'm trying not to make a lot of noise. So I'm trying to speak not too loud. Because she will come here and it will be difficult to take somewhere else. So she would want to stay here while I'm talking and all the time asking questions. So what do you do and what are you doing? That.
I see. Sometimes when I have meeting with Natif, I also see his son also.
Yes, I mean it's normal. So it's normal.
Yeah.
To to keep them under control. I was in a meeting yesterday with some representatives from the US last evening, and then she turned up all of a sudden, and her mom was distracted with the little one, and she came here and she was, oh, who are these ladies and what are they? It was funny. So she will come. You will see her for sure. I think before I finish my presentation, I think she will be here.
Okay, that would be nice to see her.
I hope that I can finish and then she can come, or at least about to finish, because if she comes halfway, it will be difficult. But anyway,
I understand.
It's more challenging than delivering a talk managing children. This is definitely more challenging.
Yeah.
How about the weather in Cordoba? Is it cold or?
Oh, it's still nice and warm. So temperature in the mid-20s during the day and a little bit more chilly at night, but it's quite nice. Very pleasant and nice to enjoy. It's overall sunny. We have a lot of sunny days. It's good. It's good here in the south. Not until mid-November. We normally have good weather.
So good season to visit, right?
Yeah, it's actually the best. The months of May, end of September, October are probably the best to visit Cordoba. So we have very pleasant weather.
In Thailand, raining every day, big rain.
Yeah, but it's still warm for you guys, so you can complain. I mean, it's nice.
Yes.
Even if it's
yesterday, flooding in Bangkok.
Oh, really?
Big rain. Yes.
Oh, yeah.
This is not good for traveler, for tourists.
For
Maybe,
sure, for sure. But this is the monsoon period for you, right?
Yeah.
So this is it's normal. I mean, it's what you can expect.
We try to welcome to tourists to travel here. Maybe in 4th November it will be better, because they allow the foreigner from 10 countries to come Thailand without any quarantine.
So the frontiers will open in November, right, for you?
Yes.
Oh, fantastic! This is amazing to hear. Okay.
But some area, right, at tourist spot, like Phuket or Pattaya or somewhere.
I can imagine, yeah. But at least, you know, it's a good news that probably very soon the country is opening already to foreigners, which is fantastic, yeah. I'm waiting for China also. So I'm planning to travel, but again with quarantine. And in there they have increased the number of days from 14 to 21. So it's 3 weeks now. So
one Chinese colleague of Professor Passer already asked the invitation letter. He planned to come Thailand.
Okay, good. But this is good. So your quarantine now is 2 weeks, I guess, like pretty much.
If they got some vaccine, they reduce the quarantine days, maybe 7 days.
Oh, good. Okay, well, 7 days is not bad if you're planning to stay for some time. But of course, it's better when the quarantine is lifted, so that you can go and enjoy the city and everything directly.
Yes, and there are some place, right? The 5-star hotel in some tourist area. You can quarantine in there and go around in the hotel.
Exactly, and you have
no need to stay inside
you
the
don't
room.
need to go outside. Yeah, you don't need to go outside. That's true. That's good for tourists. So more people are joining, I can see. That's good.
Yes, and
Yes.
And we still have a few minutes, so should be fine.
we also broadcast in the YouTube.
Oh yeah, I've seen the live in YouTube. Good.
Yep.
All right.
So some people attend through the YouTube.
Perfect. Yeah, that's fine. It's much easier anyway. So. And here is the big man. Prasad.
Hi, hello.
Good to see you. Long time no see. Everything okay?
Yes, everything okay. Maybe next year, I think maybe me, Shanatif, or the other can join. I mean, can go to Spain. We hope.
I hope that would be nice. Yeah, that was the plan originally, but unfortunately the circumstances changed. But
Yes.
that would be really great. Looking forward to your visit. Of course, you will be welcome to Córdoba.
And also in Thailand, next month we starting to open our country for foreigners. At first,
Yes, this is what Chanatip was saying. So this is fun. You know, that's fantastic.
Some of my colleagues from China will join. I mean, will come to visit us in maybe January, I think.
Okay, good. That's nice. I hope I can be back too. Yeah, for sure.
So we may get more vaccine, maybe 4th dose, 5th dose.
Yeah, well, I'm not that young anymore, Chanatip, so I was vaccinated in June. I've been vaccinated for a long time, really, more than 3 months.
How about in your country, in Spain, for the conference, is it still online or is hybrid, on-site and online?
Well, I can tell you now that you are here, because this is really great. There is the first meeting in-person event that will be held next week in Valencia. It's the National Society of Catalysis. And I'm telling you this because Jane, your student, will be attending it. So we will be paying her to attend the conference. So maybe she sent you the abstract. You have seen the abstract?
Yes, yesterday I just saw it.
So there you go. She was printing the poster yesterday. And she will be presenting, I think, Tuesday, if I am not wrong.
Okay, that's
If I
good.
recall correctly, she will be presenting, and she will be first presently in a conference. So this is the first in-person meeting after more than 2 years.
Very exciting.
Yes, she's very happy. She's very happy with it. She will go with 3 of my students, so there will be 4 from the group, including her. And they will go on Sunday, and they will return, I think, Thursday morning. They will stay there for 4 days, which is nice. They will have the opportunity not only to attend the conference, but to visit the city. And you will see Chanatip, you will see some nice photos in Facebook and Instagram for her.
Jane Facebook. Very enjoy in Spain.
Hi, Professor Guang.
Hi, hello.
Hi,
Hello.
it's
How are you?
Yes.
Yes, tell me.
Okay.
Okay. Shall we start?
Now? Okay. Yes.
Okay.
การคำนวณที่โผมันจะมีจริงๆมันมีวิธีหลักๆก็คือการคำนวณตัวคาร์บอนที่มันเก็บเอาไว้ในต้นไม้ที่ปลูกนะคะวิธีการปลูกวิธีการคำนวณเนี่ยมันมีหลายวิธีทีนี้อ้างอิงของ TGO เพราะว่าเรามองว่าถ้าเราทำในไทยเนี่ยแล้วเขาก็ทาง TGO เองเนี่ยเขาก็อ้างอิงมาจากตัว ของ IPCC ด้วยก็คือของ UN นั่นแหละเขาก็อ้างอิง
Okay, could you give show the slide? Okay. Okay. Hello everyone. Good afternoon. And today is the second day for the conference of young science on carbon resources conversion. And today we would like to give the base of our opportunity to listen to the plenary lecture from the Professor Raphael Luke. He is now the full professor at the University of Cordoba in the field of organic organica. And he also served as the editor-in-chief in the molecular catalysis. And his experience is really strong in the kind of the nanomaterials catalysis. He got have awards, many awards from started in the 2011 and for the Marie Curie Prize and Green Talented Award from Germany, and also the top 10 youngest in the entrepreneur in Spain, and also YSC Environmental Sustainability Energy Early Career Award in 2013. And recently, he got the Tanjin Distinguished Scholar from Guangzhou Normal University in 2021. He also works as a researcher in many kinds of the research, and he was named as the high cited researcher in 2018, 2019, and 2020 from the Caribbean Atlantic. And he also get the more than 30,000 citation with H index of 86 at this moment, with more than 600 publications. With he also ranking in top 1 of the all scientists in our area of expertise, and only 100 Spanish scientists in this ranking. His experience and his expert is in multidisciplinary areas such as for sure chemistry, nanotechnology, material science, engineering, and also in the entrepreneurial skill. And please welcome Professor Luke. Today he will give a present in the topic of Decline by Design Strategy for a more sustainable future, the valorization concept. Please welcome him.
Thank you very much, dear Prasad, and thank you to the organizing committee for giving me the opportunity to be here today, introducing our work that I hope you can see now in the screen, based on the benign by design strategies for a more sustainable future and revolving on the valorization concepts. The interesting thing about this topic, in fact, that you will see, is that this will, in the future, I hope, allow us to revolutionize and to change the world as we see it now, making the world more sustainable in the sense of allowing possibilities for the conversion of waste, for the conversion of biomass and carbon resources, which is the topic of this conference, into valuable end products, including materials, fuels, chemicals, and so on. So please allow me to start with a few images that reflect, unfortunately, the situation of the world we are living now. So I will keep myself quiet for a few seconds, not for a long time, and I'll let you reflect and let you evolve and evoke some memories, some thoughts. This is essentially food for thought for the youth, and we keep going in a second. What is pretty obvious from these images is that the old-fashioned model of producing, using, and disposing needs essentially to give way to a better and improved concept that requires a mindset change. This is what we have to push, what the young researchers, what the young community has to push into society, has to push into their future. This mindset change that will drive us to a circular economy in which not only reducing, reusing, and recycling should be priority words and priority terms in order to provide access to future resources for the next generations and for generations to come, including our children and our grandchildren. Also, and most importantly, the concept of valorization at the top of the pyramid that you see here. That essentially is a very relevant concept that will allow us to provide access to wealth, provide access to resources, to chemicals, to fuels, to materials, to a wide range of end products. Some of them you will see today in my presentation, by converting, by being able to harvest these values from waste, from biomass, essentially from carbon resources. So the valorization concept provides solutions, provides access to these products, while at the same time circumventing and avoiding issues that are often associated to these feedstocks, to these waste feedstocks, to these biomass. In some cases, issues that are related to odors, microbial contamination, contamination of soils, waters, and so on. So it's a double gain, because essentially the valorization concept will allow us to harvest value from waste, from biomass, from carbon resources, and at the same time avoid or minimize, in many cases even completely remove, some issues that are inherently associated to these feedstocks. And we want, of course, to be at the top of the pyramid in the concept of valorization. This is one of the main mottos for the group, for our group FQM 383, for the past almost 15 years. It's been quite a while, encompassing different research topics aimed to provide access to the valorization concept via biomass and waste valorization, but also, as Professor Prasert mentioned in his kind introduction, nanoscale chemistry, nanotechnology, nanomaterials, and catalysis. In our view, and of course from our expertise, and this is again the first take-home message to young researchers, understanding the chemical composition of the feedstock, of this waste, of this biomass, has been key to succeed in devising strategies in order to convert the different fractions into useful derivatives, into useful products, including materials, including chemicals, including fuels, and so on. The example that is illustrated in the slide is just one example that essentially highlights that understanding the different fractions, compositions of the different fractions in lignocellulosics, a semicellulosic fraction that contains C5 and C6 sugars, a cellulosic fraction composed of C6 sugars, the minor constituents that are very relevant in the case of different lignocellulosic feeds together with lignin, can provide us with different possibilities in order to devise, to design strategies for the independent valorization of the different fractions as well as, for example, in other type of feedstocks, a complete and integrated valorization or a cascade type of valorization. So there are different ways to proceed. Of course, this will be a case-to-case dependent on the feedstock, but essentially we have a wide range of possibilities if we are able to understand and we are able to comprehend what's behind the different fractions, what's behind the chemical composition of the feedstock that we are dealing with. And in this way, we have been able to provide access to a wide range of marketable products from very different residues. You see some of them highlighted in the slide, ranging from food waste all the way to plastic waste, biomass feeds, different carbon sources, into a wide range of products using essentially green technology. So we are going towards the benign by design concept, which is another important step in the valorization in order to provide access to more sustainable strategies towards such valorization. So we have employed nanocatalysis, the use of microwave irradiation, ball milling, mechanochemistry, sequential and fractionation combined with extraction in the greener ways, using greener solvents, using supercritical CO2, finding ways to make the whole process more sustainable. And the examples that in fact I wanted to bring today, for the sake, of course, of young researchers, are in fact the most updated and recent from the group. And you will see, and this is probably strange to some of you, that most of the examples that I bring today are still unpublished. So this is the last of the last from the group. And the idea is that today I will showcase a couple of, well, it's in reality 3, but 2 are interrelated. Waste to valuables, the waste to valuable concept, from food waste to valuable materials and polymers, and the use of dried sewage sludge as starting material for the next generation of bioplastics. The other example, which you will see that is nice and cool, is the waste to pharma concept, something which we started almost a couple of years back, but of course, because of the pandemic, we have been unable, unfortunately, to progress it that much. We have some nice progress that you will get to see in the coming minutes, to be able to provide access to the drugs, to the APIs of the future, starting from waste. So Daily has been actually involved in all these topics. She's an assistant professor now in a group FQN 383. And the food waste valorization concept that I bring you today is from coffee grounds to materials and useful products. What can I say at 8:15 a.m. now in the early morning in Spain? My kingdom now for a coffee. So I can assure you that when I finish my presentation, I'm going to have a nice coffee, sitting by the table with children before taking them to school and relaxing for a while. But have you ever thought what is the end point of the coffee waste grounds that you are left when you prepare the coffee? Well, we have a number of strategies to valorize these coffee grounds, and Daily in particular devised a mechanochemical strategy that you see represented in the slide to allow the possibility of designing magnetic nanomaterials which have a very strong magnetism, even a high temperature of calcination. So this is one of the first and most unprecedented magnetic nanomaterials in literature, which can retain most of the magnetism even at temperatures as high as 800 degrees C. This is very unconventional because normally the mahemite and magnetite phase, that are the two magnetics from iron oxides, are normally going and transitioning to phase hematite, which is nice because it's catalytically active, but is unfortunately not magnetic at temperatures above 400, 500 degrees C. So we managed to keep the magnetism of these materials up to 800, and this seems in fact to be related to some of the antioxidants and compounds that are present in the coffee grounds still after the extraction of the coffee. We have employed some of these materials, magnetic and non-magnetic, that you see, of course, mostly magnetic, in catalytic reactions, because the magnetic phase has also been shown to be catalytically active, particularly the mahemite phase, the iron 3 plus oxide. This is magnetic and catalytically active, and we have been using these iron-based materials in the selective oxidation of isoeugenol to vanillin, both under conventional heating and microwave irradiation, results that showed that the microwave assisted step could reduce significantly the times of reaction, as you see in the slide, from typically 24 hours required under conventional heating to just a few minutes under microwave irradiation. Here is a nice pictorial representation of an individual magnetic nanoparticle with the mahemite phase that clearly showcase the importance and the possibilities that we have in valorizing, in this particular case, food-derived waste, coffee waste grounds, into catalytically active magnetic materials. These coffee grounds could also be valorized for other purposes, and we have been using them as CO2 absorbents. So they have the capability of absorbing CO2, so are a good CO2 absorber. Another application that is not in the slide, excuse me, relates in fact to the possibility of using them as sacrificial material to generate a carbonaceous type of compound for lithium-ion battery anodes. And for this, we have a very nice publication in Journal of Cleaner Production that illustrates the potential of these materials derived from coffee waste grounds as anodes from lithium-ion batteries. And the coolest perhaps example, which we have been working for quite a few years, as you see in the patents for the group, is the use of these magnetic materials as the next generation of thermal foam for medical devices. We do have a prototype from the patent of 2017, and you see that Alina is wearing it. This is a thermally activated foam that can be in fact activated under electromagnetic radiation. So activated under an electromagnetic field, these magnetic nanoparticles spontaneously heat. They are embedded in a resin, and they provide instant heating in a part from a patient that has suffered an accident, a car accident, or any type of bone diseases and this kind of issues. So Alina is showing the prototype in the slide. The second example that I wanted to bring relates to the use of dried sewage sludge for the preparation of artificial coal. And this is one set of unpublished results in which, in fact, we could find that this sewage sludge could be converted by hydrothermal carbonization using a strong oxidant, which is the key part of the process, into a material that resembles coal. So this is why we call it artificial coal. Of course, there are several types of materials that are closer to biomass and with different properties, but we found out to our delight that we could, in fact, via relatively low temperature hydrothermal carbonization, by the use of the strong oxidant, provide an artificial coal with a high degree of qualification. And this is actually very nice because it will be the first example in literature that a coal type of material with a high degree of qualification is produced from a waste material using low temperature hydrothermal carbonization. And last but not least, the other possibility that we have been exploring from sewage sludge is the possibility of generating bioplastics. So you will see in here a short video of the composition and actually the tensile strength of the bioplastic that is created. So we are now able to generate almost transparent bioplastics from the conversion of this waste activated sludge or sewage sludge. And the interesting thing is that we hope to be able to provide a commercial material from this Chinese patent. We are doing this in collaboration with a company in the Zhejiang province in China, to be able to provide access to these very strong bioplastics for packaging and for other relevant applications. Last but not least, the last example that I bring, I'm pretty much towards the end of my presentation, is the waste to pharma concept, a concept that I mentioned that we have been developing over the past couple of years, that aims to provide access to the APIs, to the drugs of the future with different biological activities, employing in their preparation and in their synthesis, again, green technologies, including mechanochemistry, flow chemistry, microwave radiation, and so on, but with important and relevant sustainability, ecotoxicology, and techno-economic assessments of the whole process as a holistic approach. The first example that I provide here today, which is under review in ICA Sustainable Chemistry and Engineering, second round of revisions, so hopefully will be accepted soon, is the synthesis of antihypertensive type of drugs. The example shown here is ancarolol, starting from glycerol. So this is a multi-step catalytic process that we can perform at least up to step 3 in continuous flow, and the continuous flow conditions is a very simple reaction with 2-aminophenol and then subsequent amidation with the furanic derivative that we are able to obtain from biomass, normally furfural or HMF or MMF. Those are the 3 derivatives from furanics that we can obtain, we can get from humans. And the interesting thing is that ancarolol, as you see in the molecule, has a very particular feature that is derived, in fact, 60% at least of the molecule, you see the green part, from renewable resources. So this will be a nice example to illustrate the waste to pharma concept, and we are extending this concept to other furanic derivatives, including furosemide, including prazosin, and other types of molecules, antihypertensive drugs, including losartan and others. This is the pictorial representation of the concept, which is in fact a recent publication also from the group in Chemical Society Reviews to illustrate the whole concept from waste, and in particular from food waste to the pharmaceuticals, to the APIs of the future. That's in the next opportunity. I hope that I will be able to provide additional information on more molecules that we have been able to manage under the waste to pharma concept. With this, I hope I was able to convince you of the possibilities that we have in converting these resources, these carbon resources, into valuable compounds. And in fact, I'm pretty disappointed because my young researcher didn't show up. So I'm at the end of my presentation, and I was expecting for her to be here and to show the young researchers how do we lead the future and how will they lead their future. And in order to lead the future, of course, take-home message, the second and most important from today's presentation to young researchers, we lead the future being great. Of course, you have to be great, my dear students and my dear researchers. You have to be genuine and passionate about what you do. You have to be resilient, CDR, with fire, with flame. You need to be able to come back stronger and stronger after rejection of grants, rejection of papers, after disappointment, coming back stronger and stronger. You need to be able to give a bear hug many times, to be able to empathize with your colleagues, with your peers, put yourself in their skin and be able to empathize and to be able to provide solutions for some of the problems of the future. You need to be assertive, and this is also important. Stand your grounds and fight for your ideals, fight for your future. I skip the tea because I am 100% sure that the room is full of talented students and young researchers, which is all of you, and in this way the future will be yours. With many thanks again to the organizing committee for giving me the opportunity to be here. I remain at your disposal if you want any comments, any questions. We still have a few minutes in my presentation. Thank you very much.
Okay, thank you very much, Professor Rafael Roque. And it's very nice that encourage, I think, everyone that join this plenary lecture. And if anyone have a comment or a question, please raise your hand, and also maybe you can leave the message in the chat box if you are like to ask something. Okay, on the waiting, I would like to ask maybe some question on the maybe some kind of the country. I mean, in the Spain, what they are expected on the move of the maybe. I mean, in Thailand, we now focus on the CO2 as maybe because of we have the kind of a gas, and also we would like to utilize the CO2, and at the same time that as you mentioned that the waste, I think in Thailand has also a lot of waste, especially from the agricultural waste, also palm oil and cassava, something like that. How about in Spain?
Thailand is a very rich country. I mean, you have access to many resources. For us, we are a small country, Brussels, so we don't have access to so many resources. But in terms of feedstocks, I can tell you that similar to you, agricultural waste, this is one of the main resources that we have available, because the countryside is extensive here also in Spain. We don't have access to palm oil or other resources, but certainly agricultural waste, food waste, it's obviously an issue worldwide. So I think this is a most extended problem that we need to solve. I know in Asia for sure, because I have been traveling backwards and forwards many times in the past 15 years. And I have been witnessing the same issue over and over again. So food waste and agricultural waste are two of the key resources that we have, not so much CO2. There are some scientists focusing on CO2 conversion here in Spain, but frankly, I think that the largest sources of waste that we have in here are related to agricultural, to food waste, waste from oil mills, because of course we are one of the largest producers of olive oil in the world. So we do have also a lot of waste related to olive mills and the processing of olive oil.
Okay. So I think it's time, and I would like to say thank you again for your impressive presentation, and also the ways to valuable and the ways to medicine or pharmaceutical one. I hope that I can see your publication soon.
Thank you very much. Thank you, Professor.
Okay, thank you very much, and I would like to give a pause a moment.
Thank you.
Okay. Okay. Thank you very much.
Thank you.
And the next presentation we will start in 5 minutes. I mean, at 1:35. We have some maybe not a formal discussion, but it's just open for the talk. So how about the Alina?
She's already around. I can hear her and the children around. So this is why it's time for me to go and spend some time with them, get them ready for school.
Okay. So now your student also go to school?
Yes. So I need to take my daughter and my son to school. So I have to disappear now. Have a great day.
Okay.
Take care.
Okay, take care. Thank you.
Okay, take care.
You too.
Have a nice day.
Thank you. Same to you.
And
All the best for the Congress. Enjoy.
yes, and if and you would like, I mean the attendant, I mean the participant would like to publish your papers in some kind of the catalysis, please contact Rafael. He's
yes. Actually, I didn't show, but
catalysis.
anyway, this is I'm the editor-in-chief of the journal. So if you have any nice science that you want to publish, please don't hesitate to send it to our journal.
Yes, what I heard is also the reviewers, I mean all the process is really fast, right?
Yes. So this is within a few weeks normally.
Oh, it's good.
Yes.
Because the last time
we
in
have
some
been
journal,
striving to improve this in the past few years. So things are going well. Things are going well for the journal. The impact factor of next year will be pretty similar to this one.
Okay, it's good one.
All right, take care. Have a good day.
Okay, bye-bye.
You all.
Bye.
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 Okay. This session we have 7 oral presentation, and we will start with Preeti from Thammasat University. She will give a talk. Start from 1:35, a few minutes. Her topics is in the electrochemical water electrolysis using max copper oxide, sulfonated polyether ketone as the hybrid composites, proton exchange membrane for hydrogen gas production. And the next will be by Weng Li from IPE CAS. And with the topic is a high performance flexible electronics device based on metal doped tungsten oxide. And the third one is Jay Wang from Taiyuan University of Technology in the topic of a novel photoacid electrochemical switch ion exchange technology for selective recovery of bromine ion. And we still have 4 start from 2 and 5 p.m. I will give you a detail later on. Okay. Maybe it's near the time, so I would like to ask Preeti to share her research on the electrochemical water electrolysis. Please, if you are ready.
Oh, is everything okay?
Yes. The sound is good, and also the perfect slides.
Okay. Okay, good afternoon, everyone. The world is seeking for more sustainable source of energy, and we already have the solar energy, wind energy, and next comes the hydrogen revolutions. So the topic for the talk today is electrochemical water electrolysis using MSyn copper SPEAK as the hybrid composite proton exchange membrane for hydrogen gas production. And I'm Preeti, a PhD candidate from Thammasat University. And the outline of the talk includes introduction, problem and hypothesis, experimental, results and discussions followed by conclusion. The big question is, why hydrogen? Hydrogen has the highest energy content by weight of any chemical fuels and is 3 times higher than the gasoline. And hydrogen can be used in wide range of applications like the power generation, synthetic fuels in fuel cells and automobiles and so on. And in this research, I was interested on producing the hydrogen from a more sustainable and a renewable energy sources, that is the water, and breaking them into a hydrogen and oxygen. And for that, we can pass the water through a proton exchange membrane water electrolysis system and produce the hydrogen. And this hydrogen we can use as the feedstock in fuel cells and various applications and maintain a sustainable energy sources. So let's have a brief introduction about the proton exchange membrane water electrolysis. It consists of the anode chamber where the water will be passed and it will undergo oxidation with the release of oxygen and proton. And the proton will pass through the proton exchange membrane and goes to the cathode and undergo reduction with the release of hydrogen. So in this overall system, the PEM is usually designed to conduct only the proton to pass through it and act as an insulator for the electrons. And meanwhile, they will separate the hydrogen and oxygen from mixing. And here the proton transfer takes place by 2 different mechanisms. That is the Grotius mechanism, where the proton transfer from one sulfonic acid group to another and reach the cathode. And next is the vehicular mechanism, where they use water as the carrier and form hydronium ion to transfer the proton. So if you want to make a PEM, you need a material which have both hydrophobic domain and a hydrophilic domain attached to it. And we already have a commercially available well-known proton exchange membrane, that is the Nephyon, which have a PTFE backbone and a sulfonic acid group attached to it. And till today, it has become one of the widely studied material, as it have high proton conductivity and other properties like the thermal and mechanical stability, and used in various applications. But the big problem is that they are quite expensive and have complicated synthesis procedure. So I was interested on using a hydrocarbon-based polymer known as PEEK, that is the sulfonated polyether-ether ketone. They also have all the properties to be used as a PEM, but the only disadvantage is that they have low proton conductivity compared to Nephyon. And many researchers have proved that we can increase the proton conductivity by addition of a filler. And here are examples of some of the fillers that are already used to form this PEEK composite membrane, and they improve the physical as well as chemical properties of the PEEK as well as the proton conductivity. And in this work, I was interested on using a 2D material known as MSIN that stands for titanium carbide, which also have all the properties to be used as a filler, and they have high surface area and compatibility for other materials. So addition of inorganic metal oxides can improve the MSIN properties, and MSIN copper is one of the materials which has already used as a catalyst, photocatalyst for artificial photosynthesis and so on. And they also increase the mechanical stability while maintaining high hydrophilicity. Hence, my research was focused on the synthesis of PEEK, MSIN composite, followed by the preparation of the membrane, their material characterization, and various measurements of the membrane, and finally, the production of hydrogen from water using the proton exchange membrane. Here shows the overall preparations of the material. First is preparation of the PEEK from a PEEK using sulfonic acid as the sulfonating agent, and finally we can dissolve it. And next is the preparation of the composite, followed by, first of all, MSIN has been synthesized from the max phase known as titanium aluminum carbide by etching of the aluminum, and later copper has been deposited on the MSIN. And finally, the composite has been dispersed in the solution, and this membrane procedure has been prepared by a simple solution casting method and heat treated. Finally, to make it protonated, it should be treated with the acid. And after that, analysis was carried out. And first of all, this shows the XRD of the composite, and we could see all the characteristic diffraction pattern of MSIN as well as copper. And to further confirm the results, SEM was carried out and we could see a successful deposition of the copper on the layer of MSINs. And this was mainly to the high surface area of the MSIN. They provide more nucleation active site for the copper to deposit heterogeneously, and which was further confirmed by the TEM images. And from the EDS and elemental mapping, we could see the various composition of the elements, and around 20% of the copper has been deposited on MSIN. And coming to the membrane analysis part, we can see the FTIR of the membrane. And here we can see that they have the same FTIR spectra, but this shows that they are formed by a physical and an electrostatic interaction between the composite and the speak. And the only difference is that there is a slight reduction in the spectra intensity, which was mainly due to hydrogen bonding. And the cross-section of the SEM of the membrane shows that the smooth membranes become rougher if we input or put the composite inside it. And when the thermal analysis was performed through TZ and DAC, it shows that 4% has the highest thermal as well as oxidative stability, as they could maintain their weight around 98% even after 3 days, which is one of the requirements to be used in real-term application and long-term stability of the membrane. So coming to the next measurement of the membrane, which play a very important role in the proton conductivity, is the water uptake. And we can see that the water uptake slightly increases when we incorporate the composite, and the 4% have the highest water uptake, which will help in the vehicular mechanism. And the swelling slightly reduced, which shows that there is an interaction, the hydrogen bonding, which increase their dimensional stability. And from the ion exchange capacity, there is a slight decrease, which confirm the hydrogen bonding between them. And finally, we can find that the proton conductivity has improved and enhanced by the incorporation of the composite, and 4% have the highest one. And it was comparable with the Nephion 212, which is a commercially available membrane. So the 4% composite membrane became one of the potential membrane to be used as a PEM for water electrolysis. And here is the membrane that has been prepared, which is quite strong and have uniform distribution. And finally, coming to the application of this work, that is the hydrogen production from the water electrolysis system. A ice cell has been set up where we have the anode chamber and the cathode chamber separated by the proton exchange membrane, and the electricity has been applied. And the hydrogen which has been produced, the flow rate has been determined using a soft flow meter. And here is the proposed mechanism. We can see that the water will pass through the anode and proton will be transferred using our hybrid proton exchange membrane, and the hydrogen will be produced. This is the optical image of the proposed membrane, and here the overall reaction. And this work, I was interested on finding out the effect of the composite on the flow rate of the hydrogen of the speak membrane. And we can see that the flow rate drastically improved when the 4% composite was used as a proton exchange membrane, as it produced around 3.6 ml of hydrogen per minute, which was 43% higher than the speak membrane. And I would like to conclude that from this work, we have synthesized the MSIN copper successfully and used as a filler for speak to improve their properties. And various weight ratio of the composite has been loaded on the speak membrane to form the composite membrane, and 4% performs superior to all the other membrane. And when the hydrogen production was determined using an ice cell water electrolysis system, the flow rate was drastically improved by 43% comparing with that of the speak membrane, which was mainly due to the faster proton transfer and high proton conductivity of the membrane, leading to higher hydrogen gas production. And from this work, we were able to produce hydrogen energy in a more sustainable and eco-friendly way without the production of any byproducts. For this work, I would like to acknowledge my advisor assistant, Professor Suwadi, and my research unit, Catalysis, Bioenergy and Catalysis, and Thammasat University. And the talk is open for question and answer. Thank you.
Okay, thank you very much for your presentation. It's really clear. So we have a time limit. So anyone have a question? Maybe just only one question is. Maybe I would like to ask just only one question. How about the hydrogen production? That I mean, what is your target? how many moles or how many percent, I think.
Oh, in here, we try to compare the result of the pristine peak, and we set up a normal H cell using platinum as the anode and cathode. So our main focus was to know the effect of the composite on the flow rate of the hydrogen, and we can see that it's like it increased. So we proved that using this material, and this is a demo. So if using this material as a proton exchange membrane, we can produce hydrogen more efficiently.
And just only one short question from the chat box. Did you eliminate MCs before doping copper oxides?
Yes,
Okay,
we
thank you
eliminated
very much.
MC.
Okay,
Thank
okay.
you.
Thank you very much for your presentation. And the next, I would like to ask the next presenter, Wenli Lee from IPE test. Okay, the topic is the high performance flexible electrochromics device based on method of tungsten oxide. If you are ready, please give the presentation.
Okay.
And also please share your slide.
Okay. Can you see my PPT?
Yes, yes, very good. Okay,
Okay.
please start.
Hello, everyone. I am Liu Li from the Institute of Process Engineering, Chinese Academic of Science. My topic is high-performance flexible electrochromic devices based on metal-doped tungsten oxide. Next, I will introduce my reporter from the following aspect. With the progress of science and technology, the demand for energy is increasing, but accompanied by the exhaustion of energy reserves, energy conservation is particularly important. In terms of energy consumption, building energy consumption accounts for a huge proportion. At present, China's building area is 44 billion square meters, of which more than 85% is used by ordinary glass. Due to the poor insulation performance of ordinary glass, most of the building energy is dissipated through glass. Electrochromic material have the modulation of light absorption and transmission, thus reducing building energy consumption. By some estimate, a house full of electrochromic windows would need as much electricity as a 75-watt light bulb. Electrochromic is a phenomenon that materials can change optical properties reversible and low voltage. Its advantage of low cost and low energy consumption have potential application prospect in energy-saving windows and so on. At present, some problems are mainly in the optimization of production cost and performance. Therefore, it's urgent to prepare material with multiple active sets and small A diffusion distance to meet the requirement of optical modulation range, response speed, and the cycle life of devices. Tungsten oxide is a kind of indirect bond gap transition semiconductor material, which have excellent photoelectric chemical characteristics. The preparation process includes hydroximal electrodeposition and magnetron battery. Our first work was to deposit tungsten 18 oxide 49 on ITOPT. On ITOPT by hydroximal synthesis and automation pre-deposition. The uniform staggered stocking of tungsten oxide nanowells with high aspect ratio produced a larger number of hollow structures, which provided ion and electron embedding sites for electrochemical reaction. The cycle stability of tungsten oxide electrochromic films was improved from 3,000 cycles to 6,000 cycles by automation superposition. This method is a simple, low-cost transmission modulation, good cycle stability of electronic thin film preparation method. However, the material is still difficult to meet the performance requirements of devices. Therefore, in our second work, mental doping was carried out to improve the activity and stability of the material. The successful doping of nickel was verified by some technique like EDS, XRD, and XPS. The SEM figure shows that the structure of nanowells is still preserved in the doped tungsten oxide. The results show that the nickel doping didn't affect the growth of the tungsten oxide nanowells. After 1,500 charge and discharge cycles, nickel doping increases the capacity retention rate of electrochromic films from 40% to 70%. Nickel doping reduces the response time and the coloration efficiency also increased. As we know, amorphous material generally exhibit better electrochromic properties than their crystalline counterpart, but amorphous materials are unstable compared with the crystalline materials. Therefore, our third work proposed the construction of stable hybrid amorphous and crystalline material as electrochromic materials to balance and optimize the stability and activity of tungsten oxide. And the activity of material was further improved by molybdenum doping. As we mentioned above, mental doping is a strategy to enhance electrochromic performance due to the structure distortion caused by doping elements. Owing to the similar atomic structure of molybdenum and tungsten, molybdenum element was used to doping in tungsten oxide, which can introduce oxygen vacancy in tungsten oxide and consequently enhance their performance. Furthermore, the molybdenum doped tungsten trioxide electrochromic devices exhibit high coloration efficiency, fast response speed, and excellent specific energy density and long cycle life. The metal doped co-shell structure can provide a reliable solution to produce high-performance electromaterial and devices. Electromaterials are widely used in civil and military fields such as smart window display devices, car, anti-glare mirror. In order to find new application direction with universality and practicality, people are making various attempts to give electrochromic devices new features. Among them, flexibility and functional integration are attractive and practical. That's all. Thanks for your listening.
Okay, thank you for your great presentation. Are there any questions from the participants? You can open your mic or please leave the message in the chat box for the question. Okay, still waiting for the question, and I have some question on the application of the electrochromic device. On your last page, that do have many application. Which one is I think we can try first to investigate? For the application, I mean of your device.
Sorry, I didn't got you.
Please go please go to the slide, the last one.
Last one.
Yes, that one. Yeah, is the application. Smart Windows display device. Which one that you would like to test is first?
Firstly, I synthesize the electrochromic material and then assemble a devices to use in like some energy saving glasses in building and car, like a smart window.
Okay, that's good, and thank you for your answers. Okay, and thank you for your presentation.
Thank you.
Okay, the next presentation will be given by Jae Wang from Taiwan University of Technology, and the topic of the present is a novel photo assist electrochemically switch ion exchange technology for selective recovery of bromine ion. If you are ready, please give the presentation. Okay, the screen is clear.
Good afternoon, everyone. I'm Wang Jie. I come from Taipei University of Technology. At present, my work was supervised by Hao Xiaogang professor, and my title is Remove and Recovery of bromine ions by bismuth oxybromide with electrochromic switched ion exchange technology. Now I'll introduce my work from these 3 points. First is my research background. First, application of bromide. Bromine is not present in nature in its free state. It may have various oxidation levels. There in the -1 point was the most widespread. That's bromide. At present, it can be used in antimicrobial agent, fire extinguish agent, and or other chemical agents. It also present in brackish water, sewage effluent, or seawaters. At seawater, its concentration is 65 ppm. In natural water, the concentration of bromide is below 3 ppm. In surface water, its concentration is below 8 ppm, and seawater, its concentration is 6 to 78 ppm. In that light, its concentration can reach 7,000 ppm. In China, the concentration of bromide was controlled below 0.01 ppm in drinking water. If it exists in water, it can react with natural organic materials and produce bromide products such as THMS, HAS. All of this has toxicity or carcinogenity, and their toxicity is 10,000 times of their chlorinated energies. This table is the concentration of bromide in other water environment, such as sea, Dead Sea, shale lakes in Xinjiang, Leizhou Bay, or Sichuan. Its concentration in salt lakes in Xinjiang is only 10 ppm, but the concentration of bromide in Danlai can reach 60,000 ppm. So it's the removal of bromide is essential. At present, air blowing, steam distillation, reverse osmosis adsorption, and extraction was used to recover bromide. But these technologies all have some disadvantages, such as high energy consumption, high equipment inventory, and complex process, or they have secondary pollution. There in YSCRC, as a novel technology, it has some advantages such as high selectivity and high removal efficiency. Besides, it is environmental and no secondary pollution. So it was used to recover all kinds of ions. There in the removing of bromide, including two pathways. The one is absorption of bromide by bismuth oxide directly. The other pathway is adsorption of bromide by bismuth oxide, the bromide indirectly. But the pathway one didn't exist selectivity to bromide. By pathway 2, we can recover bromide selectivity. There in the bismuth oxide, bromide has these characteristics such as layered structure. That's the larger specific surface area or appropriate band gap. Besides, it can absorb visible light, and it is easy to recycle. Meanwhile, it has fast surface charge transfer rate. So we use bismuth oxide bromide to remove bromide. Therein, it can be prepared to power or film, but the power can't be used to remove bromide from wastewater directly. So we prepared the bismuth oxide bromide film by electrochemical method. Therein, in view of its characteristics, such as directly excited by visible light, we combined the electrochemical and photoelectrochemical and generated a new technology that is YSCRC. Next is our experiments. So the first step is to prepare bismuth oxide bromide film. The first step is electrochemical deposition it in carbon paper, but the carbon paper need to be treated in. So the first figure 1 is the preparation of bismuth oxide film, and the figure 2 is the contact angle of carbon paper. After treated, it has a smaller contact angle. The figure 3 is SEM or copper paper, and A is untreated carbon paper. C and D is the carbon treated paper. As so in figure 3, after treated, the copper paper has small surface, and it facilitated the deposition of the bismuth oxide bromide, and the deposited bismuth is sold in figure 4. It so that the bismuth has a structure of flower. The figure 5 is the XRD of carbon paper and bismuth. Figure 6 is so the SEM of original bismuth oxide bromide and bismuth oxide bromide after desorbing bromide or after adsorbing bromide. It can conclude that all of them has the flower shape, but the figure 6b has a contact structure that figure A and C. This was next the XID and FTIR was text to research their structure, and the XID showed that the original bismuth oxide bromide can fetched with PDF numbers 65 62, and the bismuth after desorption can be fitted with bismuth oxide. The DFT was used to research the atomic structure of bismuth oxide bromide and it's after desorbing bromide or after adsorbing bromide. The DFT showed that after desorbing bromide, the spacing interlayer of bromide is smaller. At the contact angle of bromide, bismuth bromide.
Only 1 minute left.
Huh? The DFT calculations, reply that the atomic parameter of bismuth oxide bromide has a finger spacer.
It's time. Please summarize it.
Oh, okay.
Okay, please give one conclusion on your presentation.
Oh, sorry.
Okay, it's good. Okay, that's fine. Okay, anyway, it's time. So thank you for your presentation. And due to the time limit, I would like to move to the next presentation. The next presenter is from the same university. Mengfang Jia from Taiyuan University of Technology. And the presentation title is an electrochemically induced dual size adsorption composite film of nickel MOF derivative / nickel cobalt LDH for selective bromine ion extraction. So if you are ready, please give the presentation. Okay, I see your presentation.
Can you hear me?
Yeah, sure. Please
Okay.
press slideshow.
Okay. Hello, everyone. My name is Yang Mengfang, and today my topic is an electrochemically induced dual-side adsorption composite film of nickel metal organic framework derivative nickel cobalt LDH for selective bromine ion extraction. And next, I will show you from 3 sections. Firstly, I would like to introduce the research background of bromine. As an important chemical raw material, bromine is widely used in many fields such as medicine, bactericide, flame retardant, rubber, and so on, just as these figures show. And therefore, it is of great significance to explore high efficiency and environmental friendly extraction technologies of bromide ions. In the world, bromine mainly distributes in Israel, Jordan, China, and other areas, while in China, it is concentrated in Shandong province. Look at this table. One can see that the distribution of bromine is higher in Salt Lake brine than other mediums, so we take it as our target water source. As we all know, the present state of bromine is ion. And this table is physical properties of different anions, including ionic diameter, hydrated ionic diameter, and the Gibbs energy of dehydration. We focus on bromide ion. And now the present extraction technologies of bromide, including air blowing, solvent extraction, ion exchange, steam distillation, and membrane separation. All of these technologies have their own advantages, but also has some disadvantages, such as secondary pollution, high investment cost. So we keep our eye on a novel ion separation technology, which is the electrochemically switched ion exchange. This animated picture reflects the type YSCRC process, and the YSCRC technology is environment friendly, high selectivity, and suitable for low concentration water, and the rate is controllable. In the YSCRC process, the reversible insertion and release of target ions are achieved by electrochemically switching, oxidation, and reduction states of the film electrode on the conductive substrate. And when it comes to the YSCRC technology,
The core must be the electroactive ion exchange materials. There are abundant materials reported, among them the nickel metal organic framework derivative received much attention with its porous structure, good stability, and improved conductivity compared to MOF. And the nickel cobalt LDH is also popular with its adjustable structure, high anion exchange capacity, and excellent intercalation ability. And the another reason to choose these two materials are the same metal source can provide a strong binding force for the combination of these two materials. So the next experimental section is carried out on the basis of these two materials. Look at this experimental process. The composite film electrode is mainly fabricated by the electrodeposition assisted silver thermal method. And these pictures are the characterization of these samples. First, we can see that the SEM figures and the XRD and FTIR spectra, we can obtain the conclusion that after the calcination, the flower sphere structure still maintained well. And finally, the well deposition of the nickel cobalt LDH on the surface of the nickel MOF-D film, which is also can say that the composite film electrode was fabricated successfully. And then there are the results of electrochemical tests. And we can see that from the two figures that the electronic conductivity was enhanced after the combination of these two materials, which contribute to the diffusion rates of electrons and ions increased not only in the electrode, but also in this.
一会儿这我给你发微信，好吧？晚上我告诉你个时间，我说我告诉你几点在校门口的。好吧。
Is everything okay?
Yes, everything okay.
Okay. And then, next is the extraction performance of the composite film electrode. From these four figures, we can obtain the conclusions. First, look at these figures. We can know that the composite film electrode show displayed excellent extraction performance than the single materials. And this figure shows that the 0.8 voltage was chosen as the optimal electrode adsorption potential. And the two figures below shows that the adsorption quantity of bromine improved with the increase in the initial concentration. And then is the stability and the selectivity of the composite film electrode. we can see that in the pH experiment, the results show that the composite film electrode is more suitable in the neutral solution, and the selectivity experiment was also carried out in the mix solution, and the separation factors were 4.83 and 8.29 respectively. And the two figures below shows that the stability of this composite film. We can see that after the 5 adsorption and desorption, the composite film also show the 92.7% of the first quantity, and the right part is the simulated results, and we can see that the binding energy of between different anions and LDH. We can see that the bromide and LDH, the binding energy is the lowest. So the simulated results are consistent with the experimental results. And this is a mechanism analysis. We can see that this XPS figure corresponding the main reactions of the composite film, which corresponding these figures, the first site is also electrochemical coordination mechanism, and the XRD is the XRD spectrum corresponding this equation, and we can calculate the interlayer distance. We can find that the interlayer distance is changed after the adsorption. So we can say that the two side, the second side is anion exchange mechanism. And this is the comparison of bromide adsorption ability of different materials. And through this table, we can see that our composite film electrode shows excellent extraction performance, so that our study is significant. And then finally, the conclusion is that the nickel-MOF derivative nickel cobalt LDH electrode demonstrated superior adsorption, desorption performance, and electrochemical stability because of the in situ growth strategy. And second is both the electrochemical coordination mechanism is the first site, and the anion exchange mechanism is the second site, constitute the dual site adsorption. And this study served deep understanding of ions selective extraction mechanism of LDH-based materials in the YSCRC process, which could be a novel reaction concept for the design of those electrodes with specific recognition size. And that's all. Thank you for your kind attention.
Okay, thank you very much for your presentation.
Thank you.
And due to the time limit, I would like to move to the next presenter. And sorry that I make a mistake, skip one presenter. Now I would like to ask Jiang Wei Su from Thai University of Technology to give a presentation in the topic of a novel nickel ion LDH, reduced graphene electro curry switch ion exchange film selective suppression and recovery of phosphorus. Please. Yes, I hear you. Okay. You can present now.
Hello everyone. I'm from the University of Technology. The topic of my report is lower liquor and iron. They are the double high side reduced grain oxide exchange switch ion exchange films silicate and recall of phosphorus. I will report from the follow three aspects which are research background experiment conclusion. First, the researcher background. The research first is non-reliable research. Surveys are limited and much first is route which use the production utilization process, creating concerns about future supplies and widespread environment problem. But first also has many infrastructure use such as manure. The purpose of this study is to reduce the environmental pollution caused by the excessive exchange of phosphorus and reduce the loss of phosphorus research. Traditional phosphorus removal technology. They have more loss defects. However, through the electro switch ion exchange can effectively avoid these defects. The electric culture ion exchange technology developed by our research group is a new seawater desalination technology. In this technology, the materials is deposition of the conductive matrix in a container way to prepare the member X column materials and the redox protein of the member exchange materials is controlled by using the electrochemical methods so as to achieve the reversible uptake or removal of the THN in the solution system and achieve the efficiency separation of the THN compared with traditional first phase removal technology. The regeneration cells don't not to achieve the chemical clean agent low secondary pollution able for selective separation of low conclusion Th oil to achieve the selective separation of Th ion by ESIX technology. It is necessary to propose all electrically conductor ions membrane materials that can conduct both electrons and target ions. Nearly double hydroxide as an ion not adsorbent has the purpose of ions can be exchanged between layers. However, it doesn't have extremely conductive. The excellent electric conductive of reduced Gratian oxide make up use this deficiency. Eliber the reversible insertion and remove of first ice under the condition of electric college. In this study, the hybrid materials was prepared by oil based mass. The mechanism of uptake and release of phosphorus by the mixed membrane is described in the same way. First, when the membrane electrode is given an appropriate positive pertent, the composite membrane electrode is an oxidation state. As a result, electrons are transferred from activity matter LDH to the sulfur of RDO, then transmitted to the power sample through the T-Tyler methods. The electron in the composite film electron are in the oxidized station, and the corresponding electroactive substance is activated, and the bivalence liquor and air ions will change into traverse. To balance the loss of interline loyance, first ions in the solution will be inserted to compensate for the charge loss， 然后up next further from the same figure, it can be seen LGH successful green all the ready RDO， 然后which feature prove where the materials， 然后from the XRG patterns materials was successful prepared from the XPS diagram. It can be seen the adsorption and disadsorption perfectly realized the reversible placement and remove of first ions from CV. The valence stage of materials elements change during the electrochemical radicals process of the materials, which will compense the change of YSCRC. The other
Oh, it's time. Please give a conclusion. Yes, please present the conclusion. Okay, go to the conclusion.
Can you hear me?
这个主持人说你超时了，让你把结论说一说就行了。
OK。
It's okay. Okay, anyways, okay.
Maybe he can't understand you mean.
It's okay. Thank you for your presentation. And I would like to move to the next presenter. The presentation will give by Weng Bao Ma from Taiyuan University of Technology. He will give a presentation in the topic of a conductive chlorine ion imprinted polymer treated in metal organics framework for electrochemically selective separation of chloride ion. Okay, please give the presentation.
Hello everyone. Today I will talk about a conductive chlorine ion imprinted polymers read in metal organic frameworks for electrochemically selective separation of chlorine ions. Next, I will introduce it from the following 4 parts. Chlorine ion is a common anion in wastewater. Excessive concentration of chlorine ions always leads to pollution of drinking water, salinization of soil, handling of plants of growth, and corrosion of pipeline. However, it's still for college challenge and to efficiently and selectively separate chlorine from the wastewater with coexisting ions of the same valence of all similar sub-nanometer sized hydrated iron diameters. Instead, by the working mechanism of biological protein iron channels, greater efforts have been made to develop the audit porous materials such as metal organic frameworks for highly selectively separation of ions. However, owing to the lacking of driving force and specific binding sets between target ions and functional groups, high iron deficiency and secondary pollution generated by the adsorbed rejection are still remained. To enhance the iron separation efficiency, electrochemically switched iron exchange technology based on the electroactive iron exchange material has attracted great attention because of its high selectivity, high adsorption capacity, and no secondary pollution. In the YSCRC process, the extra electric field is the main driving force for iron separation, and the reversible uptake or release of target ions can be achieved just by controlling the redox state of the material. The electroactive iron exchange material requires both electronic and ionic conductivity. Therefore, is it possible to construct sub-nanometer scale parts similar in size to chlorine? Metal organic frameworks have been considered as attractive building blocks to construct high-performance iron separation materials due to their tunable process, high surface areas, well-defined structures. The chromium-based MOF UIO66 with an effective sub-nanometer sized aperture in diameter approaching the iron size of the chlorine and stability against hashing condition has recently proven to be a processing candidate for distillation and iron separation. However, UIO66 have poor conductivity, lacking and lacking iron exchange sets, which could not meet demands of electro-iron exchange material with both electronic and iron conductivities. Polypyrrole is one of the typical conducting polymers with good conductivity and electrochemical activity. Thus, PPY could be grown in the UIO66 converted to achieve a win-win situation through a synergy effect. Next comes the experiment the prepared ULO66 was immersed into pure solution to make the pure modules entering ULO66 nanopores. Finally, the black composites after the oxidation polymerization. We obtained the following results and analysis. The quantities of ULO66 should be large enough to accommodate pure for easily filling into the nanopores. In addition, we confirmed the successful preparation of the composites by XPS, XRD, IR, and other characterization. It can be obtained from BET results that the chlorine iron imprinted polymers did not completely cover the internal surface of the material and block pore access, but 3D into the framework quantities of ULO66 without failing them. Team images also showed successful inclusion of IIP inside of the framework. The electrochemical behavior of composite film-coated electrode was invested in a 3-electrode system, as shown in Figure 9a. The smaller charge transfer restitution value of the composite film-coated electrode indeed a higher a higher conductivity with a lower electron transfer resistance. One can say that the oxidation and reduction peaks was highly symmetrical, indicating that the electrochemical reaction on this electrode should be reversible. When the initial concentration of chlorine was 3,000 milligram per liter, the absorption capacity for chlorine reached to 15.16. As stated above, such a high absorption capacity should be attributed to the more iron imprinted sites in the highly porous ULO66 and the extra electric driving force. Then the composite materials shows high selectivity. The size of the hydrated chlorine and bromines with raw free energy of hydration were close to pore entrance diameter of ULO66. Thus, size confinement in fact might attribute
It's 1 minute.
Okay.
It's 1 minute.
Attributed to highly selectivity of chlorine. The composite material is high adsorption capacity and selectivity. In addition, the structure of composite electrode was not changed according to the XRD after 1000 CV circles, indicating the composite exhibit great stability. The nanometer size quantities of UIO66 provided confined and narrow space for value change of PPY during the iron uptake release process, which effectively alleviated the volumetric stress and invaluable degradation, so that the stability of PPY was improved. In summary, that's all. Thanks for your attention.
Okay, thank you for your presentation. And also due to the time limit, I would like to move to the last presentation. Kantisha Jayen from Thammasat University. She will give a talk in the topic of development of cation exchange membrane based on sulfonated nanocrystalline cellulose and speaks. Okay, if you are ready, please show your slide.
Can you see my slide?
Yes.
Wait. And thank you for your kind introduction. Good afternoon, everyone. My name is Kantisha Jayen, and I'm a master's student from Thammasat University, Thailand. And today I would like to present for the 2021 International Symposium on Young Scholar on Carbon Resources Conversion on the topic of development of cation exchange membrane based on the sulfonated nanocrystalline cellulose and SP. And there are 5 main parts for today's presentation. And the first one is about the introduction, literature review, experimental result and discussion. And my last presentation is conclusion. And okay, let's start off with the motivation that why I want to do this work. Most of energy we consume come from the exhaustible resources such as fossil fuel, but the fossil fuel are non-renewable energy, and burning of fossil fuel create the carbon dioxide. As we know, the carbon dioxide is a greenhouse effect gas. It contributing to the global warming. So shift to renewable energy is an urgent task to prevent the exhaustion of resources. And we need to develop a stable renewable energy supply system. Among the possible solutions, hydrogen power is receiving increasing attention as a secondary energy for use of renewable energy. And hydrogen energy can play an important role in our national energy strategy with the potential for use in a broad range of applications. For example, hydrogen can be used in fuel cells to generate the electricity or power and heat, and hydrogen can be used in vehicle as well. And in this work, we focus on the produced hydrogen energy by the membrane water splitting. And the membrane in electrochemical water splitting are normally use the ion exchange membrane with a single charge, such as the cation exchange membrane. And this membrane consists of the polymer network that contain the fixed charge group. And these fixed charge group allow to transfer the mobile ion that having the oppositely charged, and they block the transport of similarly charged group. And this slide shows about the Nafion membrane. Nafion is a commercially available membrane and also the most used membrane for fuel cell and electrodialysis application. And Nafion has a PTFE hydrophobic backbone that provides the mechanical support and has the fluoroether side chain terminated with the hydrophilic sulfonic acid group that provide the proton conduction. But the price of Nafion is very expensive, low operating temperature, and many steps for preparation. And due to the disadvantages of the Nafion, significant effort have been made in the research for the new polymeric material with the proton exchange capacity as a candidate to substitute for the Nafion membrane, such as the modified perfluorosulfonic acid, alternative sulfonated polymer, or the acid-based polymer membrane. And in this work, we focus on the alternative sulfonated polymer, that is the sulfonated polyether ether ketone, or SPEAK. Actually, SPEAK have been widely investigated as a candidate to substitute for the Nafion membrane due to their lower cost, high thermal stability, and simple preparation. And for some property of the SPEAK is when you increase the degree of sulfonation, the conductivity will increase as well. But if too high degree of sulfonation, the SPEAK membrane will lack of the mechanical property and the dimensional stability. And as I mentioned before, the increasing of degree of sulfonation will lack of the mechanical properties of the SPEAK membrane. Therefore, in this work, the nanocrystallized cellulose will be added, and the addition of the nanocrystallized cellulose will be expected to improve the mechanical property and the dimensional stability of the membrane, because the nanocrystallized cellulose has many advantages such as renewable, non-toxic, high strength, and high surface area. So the objective of this work is to study the effect of sulfonated nanocrystallized cellulose inserted on the SPEAK cation exchange membrane. And let's move to the experimental part. There are two main experimental parts, which are the preparation of cation exchange membrane that consists of the sulfonation of PEAK, preparation of cellulose, preparation of sulfonated nanocrystallized cellulose, and the preparation of SPEAK composite membrane. And another main experimental part is the cation exchange membrane measuring properties that consist of the ion exchange capacity, water uptake, and the swelling ratio. And this slide shows the sulfonated of PEAK by do the sulfonated with the 98% sulfuric acid, and after that stirred at 70 degrees Celsius for 3 hours, and after drying process, the SPEAK product was obtained. And the degree of sulfonation was determined by quantitatively proton NMR, and the intensity of the proton at E signal is equivalent to the sulfonic acid group. And the degree of sulfonation can be calculated according to the ratio of the peak area of the distinct proton at E position and the integrated peak area of the signal corresponding to all the other aromatic hydrogens. And the degree of sulfonation in this work was 72%. And this slide shows the preparation of the cellulose from the sugarcane bagasse paper. This is the sugarcane bagasse paper. In the first step, we did about the delignification by adding some sodium chloride. And after that, keep stirring for 5 hours to remove the lignin out from the sugarcane bagasse paper. And after this step, the hollow cellulose product was obtained. And the second step is about the isolation of cellulose to remove the hemicellulose by using the sodium hydroxide. And after this step, the cellulose product was observed. And this slide shows the product from the delignification step, and a yield percentage from the delignification step was 97%, and the yield percentage from the isolation step was about 84%. And the final step is about the sulfonated nanocrystallized cellulose by using the 64% sulfuric acid and then stirred at 45 degrees Celsius for 25 minutes. And after freeze drying process, the sulfonated nanocrystallized cellulose was obtained. And this slide shows the XRD pattern of sulfonated nanocrystallized cellulose, and the diffraction peak at 2 zeta around 12, 20 and 22 exhibited the characteristic diffraction peak of the cellulose too. And a crystallinity percentage was about 86%. It can be calculated by the Siegel crystallinity equation. And the average size of sulfonated nanocrystallized cellulose was 280 nanometers. And this slide shows the preparation of SPEAK composite membrane by a solution casting method. In the first one, we keep stirring sulfonated nanocrystallized cellulose at a various concentration from 0 to 5%. And after that, we mix the SPEAK solution with the sulfonated nanocrystallized cellulose suspension. And the SPEAK composite membrane will observe after the immersion the membrane in sulfuric acid and die at 60 degrees Celsius. And after finishing preparing of the membrane, we need to measure the membrane properties that are the water uptake and the swelling ratio by follow this procedure. And the water uptake and the swelling ratio can be calculated by this equation. And the water uptake and swelling ratio of SP composite membrane result will show in this slide. And you can see that the water uptake and swelling ratio of the SP composite membrane were increased and higher than that of pristine SP. It can be ascribed to the combined effect of first, the adding of N-butanol could be attributed to improve the microphase separation and effective hydrophilic cluster. And the second reason is about the presence of hydroxyl group and the sulfonic acid group on the sulfonated nanocrystallized cellulose introduce the hydrophilicity in the membrane, and it leads to the availability of more hydrophilic site, and thus resulting in increasing in water uptake and swelling ratio with an increasing in sulfonated nanocrystallized cellulose concentration. And this slide show the ion exchange capacity. Again, we need to measure for the ion exchange capacity because the ion exchange capacity is another critical property of the proton exchange membrane, as it provides the information about the number of available ionic sites, which in turn affect the water uptake as well as the conductivity of the membrane. And the ion exchange capacity of each membrane was determined by the titration and can be calculated according to this equation. And as shown in this figure 5, the ion exchange capacity of the SP composite membrane were higher than that of the pristine SP because an increase in the sulfonated nanocrystallized cellulose content implies more acidic functionality in the SP composite membrane, and which lead to the increasing in the ion exchange capacity value of the composite membrane. And let me sum up about the property of the membrane at room temperature. As you can see in the table 2, the water uptake, swelling ratio, and ion exchange capacity were better in comparison to the pristine SP membrane. And these results could be ascribed to the combined effect of first, the addition of N-butanol and the addition of sulfonated nanocrystallized cellulose in the pristine SP, because the introduction of the N-butanol improved the microphase separation as well as the effective hydrophilic effective hydrophilic reagents, and the presence of the hydroxyl and the minor sulfonic acid group on the sulfonated nanocrystallized cellulose surface introduce the hydrophilicity in the membrane nature as well. And the highest water uptake, swelling ratio, and ion exchange capacity was the addition of 4% of sulfonated nanocrystallized cellulose in SP metric. And however, as you can see in the last row of this table, the decrease in water uptake, swelling ratio, and ion exchange capacity at the sulfonated nanocrystallized cellulose 5% could be attributed to the agglomeration of the sulfonated nanocrystallized cellulose, and which is lead to the lower membrane performance. And to summarize of this work, it was found that the presence of sulfonated nanocrystallized cellulose in composite membrane enhanced the water uptake, swelling ratio, and ion exchange capacity value, particularly for the sulfonated nanocrystallized cellulose and SP composite membrane with the 4% of the sulfonated nanocrystallized cellulose show the good compatibility with the sulfonated nanocrystallized cellulose and display the maximum value of the water uptake, swelling ratio, and ion exchange capacity, which is comparable to the pristine SP. And I would like to thank the scholarship from Thammasat University, the grant from the NASDA, and my advisor, Associate Professor Dr. Suridikong Palakun, for guidance and support. And that's all for my presentation. If you have any suggestion or comment, you can leave directly on my chat box. And thank you for your kind attention.
Okay, thank you very much for your presentation.
Thank you.
So due to the time limit, I would like to close this session. And if you have any question, you can leave the message in the chat box. The presenter will give you an answer later on. And the next session will be start in 3:15 p.m. In next 10 minutes. Please take a rest and refreshment and come back at the time of the next session. Thank you for your kind attention in this session.
Hi, Professor Tetsuya.
Hi. Can you hear me?
Yes.
Thank you. It's okay.
It's
Thank you
okay.
very much
Wait a
for your kind
moment.
invitation. Okay.
Yeah. Wait for a moment. 1 minute left.
Yeah, no problem.
Yes. How about in Tokyo?
Recently, number of infection people drastically decreased. So maybe more safety, I think.
Number
So
of
however,
mutate decreased too much.
Yeah. Japanese government maybe next December or January, we can start accept the foreign country student.
Very good. So maybe my student will go to Japan on January, I think.
Maybe I think so. It's okay. That's very nice.
Okay. So okay. Please, Professor Chayan, we will start now.
Okay. Okay, good afternoon, everyone. Welcome to the session 4 of Friday 15. This session, we have interesting 5 research titles. Before that, we have plenary lecture from our invited speaker. Okay, let me introduce our invited speaker. The invited speaker is Professor Tetsuya Chichido. Professor Chichido, he from Tokyo Metropolitan University. Professor focused on heterogeneous catalysis by metallic nanoparticle or metal oxide on support and by solid acid bed. Okay. He also works on in situ spectroscopic method to elucidate the reaction mechanism on heterogeneous catalysts at the molecular level. Professor Chichido, nowadays Professor Chichido published more than 250 publications, and now he also is the director of Research Center for Hydrogen Energy-Based Society and the Fellow of Royal Society of Chemistry. Okay, please welcome Professor Chichido for plenary lecture. Thank you.
Thank you. Thank you very much for your kind introduction. And first of all, I'd like to express my thanks to the organizing committee for giving this opportunity. It's my great pleasure to be here. In this presentation, I'd like to talk about the controlling the selectivity of CO2 hydrogenation by supported rhodium catalyst. The development of carbon dioxide capture and utilization, CCU technologies represent an urgent task for reducing CO2 emissions into the atmosphere and for establishing a sustainable carbon cycle. Synthesis of fuel using electricity generation from renewable sources and using carbon dioxide, such as power to liquid processes, has been proposed as a means of developing CCU technologies. In fact, the CO2-based fuels are anticipated as a technology that can increasingly incorporate renewable energy into the mobility sector as an e-fuel. For these fuel production technologies, the potential process route is Fischer-Tropsch synthesis using syngas, which include hydrogen and carbon monoxide, converted from the captured CO2. as a method of efficient conversion of CO2 to carbon monoxide through this process, reverse water gas shift reaction is a promising reaction that uses renewable hydrogen. The reverse water gas shift reaction is an equilibrium limited reaction with an endothermic nature. This reaction requires high temperatures. Furthermore, conventional catalyst reverse water gas shift processes include side reactions as presented in the methanation. This table shows the typical catalyst for CO2 hydrogenation. As you can see, rhodium catalyst showed a high methane selectivity, and the selectivity was changed by using the biometric system or alkali metal as a co-catalyst. However, to meet the criteria for implementation in industry, and the selectivity toward carbon monoxide over methane and the CO formation rate still need to be improved. Recently, we found that methane was selectivity formed on rhodium supported on niobium oxide, whereas CO was selectively formed on rhodium supported on niobium phosphate. Moreover, interestingly, CO was selectively formed on a series of phosphate support, as you can see, as well as niobium phosphate. Therefore, the selectivity of CO2 hydrogenation can be completely switched by using phosphate as a support of rhodium catalyst. This fact implies that the interaction between phosphorus and the rhodium has an important role for the changing in selectivity of CO2 hydrogenation. Up to now, the effect of phosphorus on the catalytic activity was investigated, and various mechanisms has been proposed as shown here. Machida proposed that the electron withdrawing effect of PO4 unit of phosphate support for highly dispersed rhodium species. Wang and Tang reported the strong metal support interaction between rhodium nanoparticle and the phosphate support. Kanda and Hayes proposed the formation of metal phosphate, resulting in the generation of positively charged rhodium species. So, however, the effect of phosphorus was still under discussion. To reveal the structure and the electronic state of rhodium, active rhodium species, phosphate-supported rhodium, phosphorus-loaded rhodium, and supported rhodium phosphide catalysts were prepared. The relationship between the catalyst performance and the structure and the electronic state of rhodium species was investigated. Supported rhodium catalyst and phosphorus co-impregnated catalyst were prepared by impregnation method using rhodium chloride as rhodium source and ammonium dihydrogen phosphate as phosphorus source. After impregnation, the catalysts were calcined at 1773 Kelvin. The numbers of the rhodium phosphorus co-impregnated catalysts indicate the phosphorus rhodium atomic ratio. The rhodium phosphide nanoparticles was prepared according to the literature as shown here. The catalyst was prepared by adding a support to the rhodium phosphide nanoparticle solution. Okay, next slide shows the result of CO2 hydrogenation over rhodium, phosphate supported rhodium, phosphorus loaded rhodium, supported rhodium 2P catalyst. Titanium oxide and titanium phosphate were used as a support. Methane was selectively formed on rhodium titanium oxide catalyst. On the other hand, the CO was formed and no methane was observed on phosphorus-containing catalysts regardless of the preparation method. Next slide shows the effect of reduction temperature on the selectivity of CO2 hydrogenation over rhodium phosphorus titanium oxide catalyst. The CO selectivity improved with increasing the reduction temperature. When the reduction temperature was above 673 Kelvin, the carbon monoxide selectivity reached at 100%. The next slide shows the effect of phosphorus-rhodium atomic ratio on the selectivity of CO2 hydrogenation. The CO selectivity improved with increasing the phosphorus-rhodium ratio. Now, when the phosphorus-rhodium ratio was above 2, the CO selectivity reached at 100%. To reveal the local structure of rhodium and the rhodium phosphorus titanium oxide catalyst, thus analysis was conducted. Left figure shows the rhodium KH Zane's spectra of catalyst reduced at various temperatures. Center and the right figures are Fourier transformed exhaust oscillations. As you can see, the Zane's spectra of rhodium phosphorus catalyst reduced above 673 Kelvin are similar to that of the rhodium 2P, rhodium phosphide. In FT, rhodium P bond was observed together with rhodium bond for rhodium phosphorus catalyst reduced above 673 Kelvin. And rhodium bond is slightly longer than rhodium foil. That means the local structure of rhodium is different from the rhodium foil, metallic rhodium. This slide shows the rhodium KH spectra and the Fourier transformed exhaust oscillations of the catalyst with various phosphorus rhodium ratio. The Zane spectra of catalyst with phosphorus rhodium ratio above 2 are similar to that of the rhodium 2P nanoparticles. In Fourier transforms, rhodium P bond was observed together with the rhodium bond. Also, rhodium bond is slightly longer than rhodium foil. This figure shows the crystal structure of rhodium 2P and the rhodium metal. The rhodium distance in rhodium 2P structure is slightly longer than rhodium metal. This is consistent with the Zaf's result, indicating that the rhodium 2P nanoparticles were highly dispersed on the rhodium phosphorus catalyst, reduced above 673 Kelvin, and phosphorus rhodium ratio above 2. Next, we characterize the electronic state of rhodium on rhodium niobium oxide and rhodium niobium phosphate catalyst by in situ IR. The mixture of carbon dioxide and hydrogen was introduced at different temperatures. For rhodium niobium oxide, these 3 bands were observed. Band 1 and 2 is assignable to linear CO and twin type CO respectively. Moreover, band 3 was observed above 573 Kelvin. This band is assignable to co-adsorbed carbon monoxide and hydrogen on rhodium metal nanoparticle. For rhodium niobium phosphate, the band 1 and 2 were observed. However, band 3 did not appear even at 673 Kelvin. This means that on this catalyst, this kind of species were not formed. Next, we characterize the electronic state of rhodium by CO drift IR and XPS. This band is due to adsorbed carbon monoxide. For rhodium niobium oxide, the band was observed here, and for rhodium niobium phosphate, the band was shifted to higher wave number region. Moreover, rhodium 3D XPS was observed higher binding energy region for rhodium niobium oxide and rhodium niobium phosphate. These results indicate that electron deficient rhodium species was highly dispersed on phosphate. Based on these characterization, we conclude that rhodium 2P, rhodium phosphide, is formed on phosphorus containing catalyst, resulting in the formation of electron deficient rhodium species. Next, we examined CO hydrogenation on rhodium niobium oxide and rhodium niobium phosphate. As you can see, the activity of rhodium niobium phosphate for CO hydrogenation to methane was remarkably lower than that of the rhodium niobium oxide, indicating that the CO hydrogenation was strongly inhibited on rhodium 2P, rhodium phosphide. On rhodium, by using the DFT calculation, hydrogen dissociate almost barrier-lessly, whereas on rhodium 2P, 25 kilojoule per mole is required for the hydrogen dissociation. In addition, the adsorption is destabilized on rhodium 2P compared to the rhodium metal. In particular, hydrogen dissociation is endothermic because it is unstable after dissociation. This is stabilized by hydrogen diffusion on a certain extent and become exothermic. But when the coverage of hydrogen is high, diffusion is also suppressed, and hydrogen dissociation becomes thermodynamically unfavorable. As described above, hydrogen adsorption and dissociation in rhodium 2P are considered to be kinetically and thermodynamically unfavorable compared to the rhodium metal. The adsorption of CO is slightly weaker on rhodium 2P than rhodium. The dissociation on CO of CO, which is necessary for methanation, methane formation, is likely to occur at the terrace site due to the extremely large activity barrier. At the step site, the all-atom adsorption site are sterically closed, which gives geometrical advantage and lowers the barrier significantly. In other words, the CO dissociation is structure sensitive. On the other hand, in the case of rhodium 2P, the barrier is not as low as in the case of rhodium, and as a result, CO dissociation is also suppressed. This result indicates that the formation of phosphide decreases the adsorption and the dissociation capacity of the hydrogen, and promote the desorption of the carbon monoxide and suppress the dissociation. The combined function of these factors is thought to inhibit methane production, and selectivity produce CO. In conclusion, we found that rhodium 2P was formed on phosphorus-containing rhodium catalyst. CO and hydrogen adsorption and dissociate on rhodium 2P nanoparticle was unfavorable compared to rhodium nanoparticle. The CO hydrogenation was slightly strongly inhibited. Therefore, on phosphorus-containing rhodium catalyst show a high activity and selectivity in reverse water gas shift reaction. So finally, I'd like to thank the member of our laboratory and this financial support. Thank you for your kind attention.
Thank you, Professor Shido, for your plenary lecture. Is in town, very in town. Okay, I would like to know, Professor, in Japan, have any rhodium catalyst application in scale up?
Yes, of course. So recently, the several kind of reaction were tested by the several kind of phosphide catalyst.
So that from your slide, it seems that we need a lot of I'm not sure, a lot of hydrogen for to be the reactant in your reaction?
Yes, of course. The hydrogen production is an important problem. Usually the electricity is required to form the hydrogen. So this is a green hydrogen. And CO2 separation from the atmosphere or exhaust gas from the industry or cars. So combined with this carbon dioxide and the green hydrogen should be converted to the should be used for the CO production and methane production. Depend on the situation.
Okay. It's really interesting. It's different from my research. I try to capture the CO2, and this is the better way for use the CO2 for the methane. Okay. Thank you very much, Professor.
Thank you very much. Thank you very much. Sawadee krap.
Okay. The next. Okay. The next title is the framework structure phosphate with the metal as catalyst for the ethanol conversion. The speaker is Diana Osulenko from Friendship University of Russia.
Hello.
Please. Okay. Okay, I see you slide.
Okay, good.
Yes.
Good afternoon, dear colleagues. The topic of today's presentation is framework structured phosphates with their metals as catalyst for the ethanol conversion. At first, I would like to introduce myself. My name is Diana Saulenko. I am a first-year PhD student. I'm a representative of the People's Friendship University of Russia, namely the Department of Physical and Colloid Chemistry. The research was carried out with in collaboration with our colleagues from Lobachevsky State University of Nizhny Novgorod. So in recent years, the processes of energy production using green sources such as hydropower, wind energy, and biofuels have received significant attention and significant development. Bioethanol obtained as a result of fermentation of biomass is a liquid biofuel and potential source of combustible hydrocarbons. Processing of bioethanol into organic compounds and their mixtures with improved fuel characteristics is considered promising. In addition, ethanol is a raw material for the production of ethylene, 1,3-butadiene, 1-butanol, hydrogen, diethyl ether, and a wide variety of hydrocarbons. So in connection with development of catalytic conversion of ethanol, scientists face the task of finding the appropriate catalyst for this process. Catalytic systems such as zeolites and mixed oxides are being actively studied. The complex phosphates with an second structure from our point of view are also promising catalysts for this process. The phosphates with second structure have a skeleton structure consisting of angled tetrahedra PO4 and octahedra LO6 and has two types of voids. The alteration of these voids forms the conducting channels and forms a three-dimensional grid where the ion transfer is carried out. These compounds have thermal stability and flexible structure, which make it possible to vary the chemical composition. This in turn allows to regulate the acid-base or redox properties and thereby obtain catalysts for the desired purpose. Also, compounds with such a structure are widely used in industry as fuel cells, sensors, electrodes, and ceramics. Depending on the composition, the crystal structure of mesicon family can be represented by various structural types. The most common of them, NZP type, based on the structure of sodium zirconium phosphate, and SV type, the type of scandium tungstate. So on the catalyst of the sequence structure, the conversion of ethanol usually proceeds in 3 directions: intermolecular dehydration with formation of diethyl ether, intramolecular dehydration with formation of ethylene, and dehydrogenation with formation of acetaldehyde. In this work, double phosphates was synthesized and studied, including double phosphates of magnesium, scandium, strontium, cadmium, lead, cobalt, nickel, manganese, and calcium. The study samples were synthesized by Zorkel method according to the scheme and characterized by various physical-chemical methods. The catalytic activity was studied in the ethanol reaction in catalytic unit, followed by gas chromatographic analysis of products. It turned out that radiographs of all single-phased samples are similar in position and intensity of reflexes and indicate that they belong to the structural type of NZP or SV. The X-ray phase analysis data are confirmed by infrared spectroscopy data, which indicate the absence of amorphous impurities in the samples. The chemical composition also confirmed by electron microscopy and microprobe analysis. The nitrogen absorption and desorption isotherms of all samples shows the presence of mesopores. For samples with NZP structure, the specific surface area and pore diameter available for adsorption increased with increasing of the ion radius. Catalytic experiment shows the activity in direction of ethanol conversion. The total conversion reached 65% and didn't depend on the type of phosphate structure. However, the selectivity varied depending on the condensator ion. The maximum of total conversion of ethanol increases in the series manganese, nickel, magnesium, strontium, cadmium, lead, and cobalt, which correlates with the specific surface area in the series of samples. The selectivity of products significantly varied and depended on the temperature, the nature and number of the catalytic centers, and nature of compensator ion. The nature of the compensator ion strongly influenced the catalytic characteristic, thus the yield of ethylene on NZP samples correlates with the value of specific surface area of phosphates and increased in the series cadmium, strontium, lead. In the case of double phosphates with the SV structure, the selectivity for intramolecular dehydration increases with increasing of the modifier ion radius. As is known, the dehydrogenation reaction usually proceeds by the redox mechanism. The data we obtained on NZP phosphates confirm this. For NZP phosphates, with increase in the ionization potential of compensator ion, selectivity for dehydrogenation increases. For SV samples, we observed a correlation of selectivity with reduction potential of the compensator ion. Also, we studied the samples in which the zirconium ion is replaced by titanium ion, which has a smaller radius, in anionic part of phosphate. It can be seen when the type of structure changes, the volume of crystallographic cells increases. At the same time, the specific surface area of the sample with titanium decreases by 2.5 times. Also, the samples show a shift from the process of intermolecular dehydration with the formation of diethyl ether to intramolecular dehydration with the formation of ethylene. Next, we studied the triple phosphates of manganese zirconium and calcium zirconium doped with nickel in various amounts. According to X-ray results, solid solutions are formed in these samples. The addition of third ion increases the surface of NZP phosphates and reduces the surface of sweet phosphates. The main reaction on these samples was acetaldehyde, the main product, sorry. This ethylene and DTLF proceeded with smaller yields. For manganese phosphates, the introduction of nickel doesn't change the overall conversion of alcohol, but significantly changes the selectivity. Acetaldehyde selectivity considerably increased with X grow in the samples. The overall conversion of calcium compounds decreased with increasing of X of nickel amount in samples, presumably by reducing conversion to aldehyde. Based on this data, it can assume that the number of reaction centers simultaneously decreased. Thus, the zirconium plus 4 ions were involved in the formation of the catalytic centers. The calcium plus 2 and nickel plus 2 ions doesn't involve. Comparison of the data obtained on the two-study system, we propose that acetaldehyde forms on the active centers forms by zirconium plus 4 and manganese plus 2 ions. So the highest selectivity for acetaldehyde formation was on double calcium zirconium phosphate and triple manganese nickel zirconium phosphate. For calcium zirconium phosphate, it be considered a selective catalyst for producing acetaldehyde at 400 Celsius with a yield of 55% of theoretical amount. As we can see, this percentage is much better than used for the halides and mixed oxides, but worse than for catalysts containing vanadium and molybdenum and precious metals. So thereby phosphates with Nichicon structure are active and stable catalysts for ethanol conversion, and their modification, the introduction of third ion, presents the possibility of obtaining selective catalysts.
I'm sorry, Ms. Diana, please summarize your words. Now time up.
I'm already in the presentation. So then doping the ions, we can change the selectivity for other products as well. So in the end, I would like to express my great heartfelt gratitude to the organizers of the conference for the opportunity to have a participation in this conference. It is an honor for us to present our work in this symposium. Thank you for your attention. We will receive feedback. Greetings from Russia.
Thank you, Ms. Diana. It's interesting your words, but now time up. So we have to move on to the next presenter.
Okay.
Thank you.
Okay. Thank you.
Thank you. Okay. Let's go to the next presenter entitled of catalyst nickel molybdenum calcite with infrared heating for hydrodesulfurization of shale oil from Mengchuan Chang from Shenyang University of Chemical Technology. Okay. Hello. Let's start. Mengchuan Chang. Okay. Okay. It shows. I cannot see your voice. I cannot. Nothing now. Okay. Let's start. I can't hear your voice. Any sound? No, any sound. It seems you have some problem about your computer.
So maybe same as yesterday. Maybe we may skip to next speaker, and after that we have to solve some technical problem.
Okay. So we have to skip the next for the next presenter.
Okay. We can hear you now.
Okay.
Yes. Okay. Let's start.
你先让他。那行。跳过了吗？ 说一下。你在这儿，来这儿。
Hello.
Yeah, I can hear.
可以了。那这个可以了。Can you hear me?
Yes, I can.
没有声音啊，听着。
你说呗 ，Can you hear me?
Can you hear me?
Yes, I can.
但这个里面声音很小，其他人不。
把声音开大。
Let's show you a slide.
Okay, is it okay?
Okay, I can see. Good, very good. Okay, let's start the presentation.
Okay, good afternoon, experts and scholars.
Okay.
My name is Zhang Mengzhen from Shenyang University of Chemical Technology. My report title is nickel-based catalyst calcite with infrared heating for hydrodissociation of shale oil. I will introduce my report from the following aspects. Oil shale belongs to unconventional and oil and gas resources with abundant solid organic matters and can be pyrolyzed to obtain shale oil. It's a potential crude oil alternative for its considerable amount of resources in the world. Therefore, it's necessary to upgrade shale oil. However, its high heteroatomic content hinders its direct use as crude oil. Therefore, it's necessary to upgrade shale oil, especially to lower its sulfur content to meet various refinery feedstock specifications. There are not of desulfurization methods to upgrade shale oil. Hydrodissociation and oxidative desulfurization have been used extensively to reduce sulfur content in the world. Inside, hydrodissociation technology is relatively mature and effective. Catalysts plays a key role in catalytic hydrodissociation reaction.
There are many kinds of hydrogenation catalysts, like Ni-based and CO-based catalysts are most widely used. However, not some problems exist. There are many problems in the catalytic process, like carbon depolation and deactivation. Deactivation are urgent problems for hydrogenation catalyst. In this part work, I tried to prepare catalyst with hair catalytic activity and hair resistance to cooking. Two catalysts were prepared. One was prepared by conventional heating. Another was prepared by infrared radiation method. The infrared radiation heating can penetrate into the surface to the heated material to a certain depth, but almost don't hit the media in the heated space. So it has advantages to of the high thermal efficiency. It can raise the temperature instantly. The heating speed is 300 times higher traditional heat than conventional heat treatment. HRTM calculations show the particle size distribution for surveyed CH catalyst is 5.4 to 7 m. For surveyed CH catalyst is 1.8 to 2.6 nm. The high rate infrared radiation heating in catalyst cancellation enabled the yield of catalyst with a higher degree of mental disparity. SRD and the TG characterization proved after reaction cook deposits on the catalyst. It can be seen from the TG characterization that the spent air catalyst, the air witness is 80.5% for 20.7%. 7% for spent CH catalyst. So indicating spent air catalyst had higher resistance to cooking. As expected during catalyst stability evolution, it's found that the surveyed IR catalyst constantly produce the non-sulfur containing oil, varying high HDS activity of the former. After testing for 110 hours, the sulfur content of product oil is stable at 2,500 ppm at 308 degrees. And 2,100 ppm at 400 degrees. While the sulfur content of product oil is stable at 4,200 ppm at 380 degrees.
and 4,000 ppm at 400 degrees. Also, the product oil obtained for IR catalyst show hair with heating value and lower sulfur content, lower viscosity. In short, this infrared radiation can improve catalyst activity, more oxygen defeat sites, and hair resistance to cooking. The most appropriate operation conditions, temperature at 380 degrees, pressure is 4 MPa, and film ratio is H2 to oil film ratio is 600. LHSV is 4 per hour. This last the upgraded oil has met the national marine fuel oil standard. That's all. Thank you for your attention.
Okay, thank you. Meng Chuan Chang. Hello. We have time for a question. Have any question from the first participant? I think it's very interesting your work. Try to remove sulfur, right, from shale oil.
Yes.
And I would like to know the I'm not sure the slide number is about advantage and disadvantage for your method. Please show the slide, maybe number 4. Number 4.
Number 4.
Yeah.
Okay.
Okay. In this research, you use the hydrodesulfurization, right?
Yes. Yes.
And what is the disadvantage? What is the disadvantage for your work?
For
low, I cannot see. It's low, so it's lower the sulfur content.
The disadvantage for hydrodesulfurization method. Okay. Hydrodesulfurization method technology, in fact, is very effective, but it's very for the catalyst is very it's easy to deposit cook on the catalyst surface.
Okay.
So this part of work we try to solve this cooking deposition problem.
Okay. I can see you're right on this slide. Okay. Thank you very much for your interesting research. Thank you very much. Okay.
Thank you.
Bye. Okay, the next presenter in the title of catalytic oxidative hydrogenation of oleic acid to long-chain bio-olefin over vanadium manganese oxide, KIT6 catalyst, by Mr. Duiller from Chulalongkorn University. Okay.
Hello, everyone.
I can see your slide.
Can you hear my voice?
Yeah, I can hear.
Okay, that's good.
Very good, clear. Okay, let's start.
Thank you. Yes. Okay, good afternoon, everybody. My name is Ville. I'm come from Chulalongkorn University, and today I would like to share about my research focusing on the production of long-chain bio-olefin from the oxidative dehydrogenation of oleic acid using the vanadium magnesium oxide KIT6 catalyst And this is the outline presentation. As we know, olefin, including the alpha and the internal, are the key intermediates widely used as the conomer for production of polymer, surfactant, detergent, oil field chemical, and lubricant oil, depending on their chain length. However, olefins are mainly produced from fossil resources via the catalytic oligomerization of ethylene or by the dehydrogenation of alkane from the feature chop processing. With the depleting of the fossil resource, the use of the renewable resource to reduce the olefin is increasing interest. Fatty acids is expensive and available, which can be obtained from the renewable resource, are considered as the renewable feedstock for reducing the olefin. Several methods has been reported for synthesizing olefin from the fatty acids, for example, the olefin metathesis via the cell metathesis or the cross metathesis of the fatty acids with the ethylene by using the homogeneous ruthenium-based catalyst. However, only unsaturated fatty acids are available and the homogeneous catalyst limitation remain. The other method is the deoxygenation of fatty acids. However, the inner atmosphere and the additives such as the acid anhydride and the phosphide ligand are required to achieve the best catalyst performance and selectivity. Alternative, the oxidative dehydrogenation of alkane is the valuable and acceptable to reduce the olefin from alkane. This is the thermodynamic favorable at the low reaction temperature and usually do not lead to the formation of coke. However, it is essential to prevent the over-oxidation of the desired olefin to combustion products. Although the oxidative dehydrogenation of alkane has been exploited to reduce the white olefin from short chain to medium chains, the production of long chain olefin has not been robust yet. So therefore, in this research, we would like to reduce the long chain olefin from the oxidative dehydrogenation of oleic acid by using the vanadium magnesium oxide KIT6. Why we select this catalyst? Because this catalyst is the combination of the vanadium, which is considered as the wood metal catalyst for the oxidative dehydrogenation, and the magnesium oxide is the basic, and it can interact intensely with the vanadium to inhibit the formation of oxygen and the small hydrocarbon. KIT6 is the 3D mesoporous silica with the high surface area and the large pore volume, which can be promote the dispersion of the vanadium. The catalyst was prepared by two methods. The method one is the one-pot synthesis. So in this method, the vanadium was incorporated with the magnesium oxide and the KIT6 by direct hydrothermal. And the catalyst was prepared with the different molar ratio of the magnesium and the vanadium from 0 to 1.5 molar ratio at the constant vanadium to silicon equal 0.05. And the second method is the impregnation method. The magnesium oxide KIT6 was synthesized first, and then the vanadium was both loaded on the magnesium KIT6. The different vanadium content from 0 to 9% weight was loaded on the magnesium KIT6. The catalyst characterization, the XRD and the TEM image results show that the other mesoporous structure of the KIT6 was remained in both the catalyst prepared by one-pot synthesis and the impregnation methods. The nitrogen isotherm of the catalyst prepared by one-pot synthesis show the type 4 with the S4 synthesis loop. In contrast, the type 4 with S1 hysteresis loop was observed for the catalyst prepared by the impregnation methods. The hydrogen TBR of the catalyst prepared by one-pot synthesis show that without magnesium oxide, the vanadium KIT6 show the two reduction peak. The first peak at 590 degrees C corresponding to the isolated vanadium oxide, and the second peak at 675 degrees C according to the unsaturated coordination of the vanadium oxide, and with increasing the molar ratio of the vanadium of the magnesium to vanadium, the second peak decrease and disappear, indicates that the highly incorporated of the magnesium with the vanadium oxide. In contrast, the hydrogen PBr of the catalyst repair by impregnation method show only one reduction peak corresponding to the isolated of the vanadium oxide. The SPS spectra of the selected catalyst repair by one post-synthesis and impregnation method show only one peak. This indicates that most of the vanadium was presented in the V3 plus oxidation stage, and the catalyst was applied for the oxidative dehydrogenation of oleic acids. The reaction was carried out in the feedback reactor as shown in this scheme, and this shows the reaction condition. The obtained products from the reaction, including the liquid products and the gas products. In the liquid products, it consists of the water phase and the organic phase. So this slide shows the result of the catalyst performance. So it can be seen that the catalyst exhibits the excellent performance over the conversion of oleic acids. The highest oleic acids, over 90%, can be observed at the 0.5 magnesium oxide vanadium K86 repair by one post-synthesis, and the highest oleic conversion can be observed for the catalyst repair by impregnation at 1 to 3% loading. The organic phase obtained from the reaction was analyzed by the GCMS, and the component was divided into the alkene, diene, alkane, aromatic, cyclic, and oxygenated compound. And we can see that the highest selectivity towards the alkene was observed for the catalyst repair by one post-synthesis at 0.5 magnesium oxide vanadium K86 with the minimum of the oxygenated compound. Similar, the result was also observed for the catalyst repair by impregnation at 1% weight of the vanadium with the selectivity to the alkene about 40% and the minimum of the oxygenated compound around 13%. And the distribution of the carbon atom in the liquid products of both catalysts show that the major alkene products was in the range of the C10 to C17, while the larger C17 compound was the oxygenated compound. So for summarize, we have demonstrated that the production of long-chain olefin from the oxidative dehydrogenation of oleic acids using the vanadium magnesium oxide K86 catalyst, and the olefin selectivity was strongly influenced by the magnesium vanadium molar ratio in the one post synthesis and the content of the vanadium loading in the impregnation methods. Both the catalysts 0.5 magnesium oxide vanadium K86 and 1 vanadium magnesium oxide K86 show the highest performance for olefin selectivity with the alkene and diene about 52%. So I would like to thank Professor Nabida Hinchiranas, and thank you very much for your kind listening.
Thank you very much, Mr. Duiller. Okay, I would like to know in your slide number 11.
Yes.
I don't know the difference between liquid product and organic phase. What is the difference?
In the liquid products is contain the water phase. The bottom is the water phase and the upper is the organic phase. So we got the products we separate, and the organic phase was analyzed by the GCM.
Okay, organic phase is the liquid you separate from liquid or product.
Yes, yes. This water
Okay.
phase.
Okay, thank you very much for your presentation.
Yes, thank you very much.
Okay. Okay, for the next presenter, in the title of Development of Nickel-based catalyst for polymerization for ethylene to jet fuel by Ms. Pratya Panpian from Thammasat University. If you're ready, let's start, Ms. Pratya. Okay.
Okay, everything is okay, right?
Yeah, I can see your slide. Okay, your voice is clear. Okay.
Okay. Good afternoon, everybody. My name is Pratya Panpian. I am a master degree in Thammasat University. Today, I would like to talk about the development of nickel base for the decarbonization of ethylene to jet fuel. This slide shows the content I will present today. Okay. Development of jet fuel. Development of technology make transportation very easily. The jet pan, which is the one of the method that is faster and convenient. The jet fuel is a mixture of a large number of the different hydrocarbon, and when demand of jet fuel is increasing, the natural resource fossil fuel were used to produce the jet fuel, which are non-renewable resources were used to produce the jet fuel. Moreover, reaching to the global warming. And one choice is the oligomerization of ethylene, which can produce the jet fuel, where ethylene can be produced from the bioethanol. And in this process, I use the ethylene undergo oligomerization using the homogeneous catalyst to give the jet fuel and gasoline. But the homogeneous catalyst have a limitation. The limited is difficulty in the separation from the product and limited use. Sensitivity to impurity, so heterogeneous catalyst is come up. And this slide show the difference of the catalyst in this process. The first generation, they use a nickel MCM22. And, sorry. Okay, and nickel MCM36, the property in this work is the micropore and one-dimensional structure. In the second generation, they use the nickel SIR-AL30. The property in this generation is the mesopore and two-dimensional structure. So in this work, I use a nickel alumina KIT6 catalyst because the property is the mesopore and three-dimensional structure. The okay, structure will the result, the substance coming out of the porous. The porous is the pore quickly as can increase the rate of the reaction. The objective in this work used for the development of the nickel catalyst for oligomerization of ethylene to produce the jet fuel. To study the ethylene reaction over the nickel alumina KIT6. Okay, to study the effect of silica alumina ratio, percent nickel in the continuous feedback flow reactor on the ethylene conversion and the olefin distribution. This slide shows the preparation of the KIT6. First, use the Pluronic P123 and the water, add the hydrochloric 37% and add butanol and triose. After that, go to the hydrothermal. The product was filtered and washed and dry and calcined. We'll get the KIT6, and after that, the KIT6 dissolved in the water, add the sodium aluminate. After that, filter and wash, dry at 80 degrees C and calcine at 550 degrees C. We'll get the sodium alumina KIT6. Use the sodium alumina KIT6 dissolved in 0.5 molar ammonium nitrate. For filter, after that, filter and wash, we'll get the ammonium alumina KIT6. Use the ammonium alumina KIT6 nickel resonate impregnation with the nickel nitrate and dry at 80 degrees C, calcine at 550 degrees C. We'll get the nickel alumina KIT6. In this slide, show the physical chemical property of the catalyst prepared in this study. The silica alumina ratio of the can characterization by the X-ray fluorescence, and the ammonium alumina KIT6 ratio 5, ratio 10, and ratio 15. When after characterization, show the silica alumina ratio 8 and 7, 11 and 17. The BET surface area first, the KIT6 allow 829. When I add the nickel and alumina, the surface area is decreased around 200 and 400. The pore diameter when the KIT6 allow 8, and when I add the nickel and alumina, the pore diameter decrease around 7 and 6. This slide shows the diffraction, X-ray diffraction, the X-ray pattern of the KIT6 which correspond to 211 from this one and 220 and 3T2, the plane of the KIT6 temperature. Moreover, which show can be seen in the two data lengths of 1 to 2 degrees, which are characteristic of the mesopolar structure of the KIT6 temperature. Didn't change after modified by illumination and alumina ratio 5. The X-ray pattern show the KIT6 temperature is catching because the high acidity. This slide show the TEM image. This one is show the nickel when I add by impregnation, and this one show the temperature of alumina KIT6 when I add the nickel. The temperature it didn't change when I add the nickel. And this slide show the reactor system. First, use the ethylene and nitrogen for 2-mass flow controller and go to the reactor system. And go to the reactor with catalyst and control the temperature by temperature furnace. After 6 hours, we'll get the product to two phase. The first phase is the gas analyzed by GC, and the second phase is the liquid phase analyzed by GCMS. The parameter of the jet fuel production. I use the ethylene 99.99%. The weight has spread velocity around 0.5. The flow rate of nitrogen allow 10 milliliter per minute, and the flow rate ethylene allow 15 milliliter per minute. The temperature allow 300 degrees C. The pressure allow 20 bar. This slide show the effect of silica alumina ratio. The silica alumina ratio 10 is show the ethylene conversion CX plus selectivity and liquid hydrocarbon yield higher than the silica alumina ratio 15 because the silica alumina ratio 10 high acidity than silica alumina ratio 15. But when I add the acid site in the silica alumina ratio 5 more than ratio 10, but the conversion and CX plus selectivity and liquid hydrocarbon yield is decreased because the silica alumina ratio 5, the acid site is higher, and the temperature of the KIT6 is catching. This slide shows the effect of percent nickel. The percent nickel, I increase the percent nickel, and the ethylene conversion CX plus selectivity and liquid hydrocarbon yield also increase. The percent nickel 6 show the stable for the 6 hours more than the 2% and 4%. That indicated that the nickel as important. The nickel is important fraction for use the ethylene to produce the jet fuel. And the conclusion in this work, the nickel alumina KIT6 is promising the catalyst for biojet fuel produced towards the ethylene oligomerization, and the catalyst is the nickel alumina KIT6 ratio 10 exhibits close to the 90 conversion and result in the product distribution, which offer the highest amount of the total CX plus selectivity around 45.3% and liquid hydrocarbon yield around 43.65%. Okay, I would like to thank Associate Professor Dr. Chanatip Samad and Dr. Lalita Atanato and our group lab member. Thank you for your kind attention.
Thank you. Thank you, Miss Patria I would like to know what is your product? Jet fuel.
Yes, jet fuel is the CX plus hiring.
Okay.
CX plus. Yes, maybe that maybe CX plus selectivity is the important for this work.
From this table,
yes.
what is your product? Liquid.
Liquid phase and
phase.
the gas phase combined with together. You see in the peak in the.
Okay, so the important effect for your work is the silica alumina ratio.
Yes, and
nickel percentage. Okay.
Yes.
Okay. Thank you.
Thank you.
Very interesting. Thank you very much. Okay. Okay. The last presenter for this session is the title of highly selective hydrogenation of furfural to furfuryl alcohol calcium modified copper silica oxide catalyst by Debao Li from Shenyang University of Chemical Technology. Okay. If you ready, let's start. Okay.
Can you hear me?
Yes, I can.
Okay.
Okay,
So,
very clear.
I would like to give an explanation because Dr. Li Debao, something come up, so he had to attend another conference. Another doctor will give another presentation to replace it. Is it okay?
Okay.
Okay. Done.
Okay. Good afternoon, everyone. My name is Yizheng Li from Shenyang University of Chemical Technology. The topic of my report is carbon dioxide and methane reforming over nickel oxide and gamma alumina in fixed or fluid bed multi-switching mode and high concentration carbon dioxide. And the first part is introduction. Carbon dioxide and methane reforming combines two of the most problematic greenhouse gases to generate synthesis gas, and therefore is an appealing reaction for control of global warming. Nickel is chosen most often as the active component in catalytic reforming catalyst due to its wide availability and low cost. Coke formation is a major problem in performing the reforming reactions over nickel-based catalysts. How to suppress or minimize the carbon formation that has been the main concern of studies of the reforming reactions. Most of the studies have focused mainly on developing cooking-resistant catalysts, but a few have approached the issue from the aspect of optimizing the conditions of the catalyst bed. Considering the highly endosmic characters of the reforming, one might choose an isothermal operation for carbon dioxide reforming of methane. For this, in the present study, we designed a new operation mode of multi-mode switching of fixed or fluid bed for investigating carbon dioxide and methane reforming reactions ended at different times and in different modes to examine how the fluid bed operation minimize the carbon deposition in the present reforming reaction and whether a change in bulk or surface structure or changes in properties of the catalyst also occurred. The effects of the fluidization of catalyst bed on carbon dioxide and methane reforming were explained and are discussed further. And then is the experimental The catalyst was prepared by immersion of gamma aluminum using an aqueous solution of nickel nitrate. The sample was then calcined in air at 823 Kelvin for 4 hours. The 2% of nickel loading in the catalyst was determined by measurement of bond compositions using ICP-AS. Carbon dioxide and methane reforming was performed in a coarse macroreactor that can be operated in either fixed or fluid bed mode. Feeding the reactant gases down or up flow, but the catalyst bed in fixed or fluid bed mode. Well mode switching was realized by a four-way valve placed on the feed line before the reactor. And the result is as follows. Carbon dioxide and methane reforming in a single fixed or fluid bed switching mode. An experiment of the single mode switching from fixed to fluid bed was carried out as follows. First, the reforming was performed in fixed bed mode for 3 hours to confirm that the activity of the catalyst bed indeed becomes stable during this period. And secondly, the mode switching was conducted for another 2 hours, fluid bed reforming. As shown in the figure 2, the mode switching operation led to a significant increase in methane and carbon dioxide conversions, while the subsequent fluid bed operation maintained the conversions and hydrogen or carbon monoxide ratio stable at high levels till the run was stopped. This result clearly indicates that fluid bed operation is effective to improve catalytic reforming performance of the catalyst. Furthermore, in order to investigate whether such an improvement resulting from the fluidization of catalyst bed can reproduce during the mode switching reforming, we designed a continuous fixed or fluid bed multi-mode switching experiment and performed it under the same conditions as those used in the single mode switching experiment. And this is the carbon dioxide and the methane reforming in a fixed or fluid bed multi-switching mode. The multi-mode switching reforming test was carried out in the following way. Firstly, fixed bed mode, followed by fluid bed, then fixed bed again, and finally fluid bed mode again. As the figure 3 shows that the time depends of methane conversion. The results of the reforming reaction at different time courses of the different modes are summarized in table 1. And it can be seen from figure 3 that methane conversion showed a great jump with the first mode switching from fixed to fluid bed operation. The jump was about 44%. It's about from 48 to 92%. Then a drop from 19.2 to 75% followed with the second mode switching, reversely from fluid to fixed bed 1, followed by the second jump with the third mode switching from fixed to fluid bed operation, which was 14%. It's about from 75 to 89%. In addition, the second jump was always smaller than the first one. As shown in figure 3 and table 1, the methane and the carbon dioxide conversions, as well as the hydrogen and the carbon monoxide ratio were essentially recovered in the final fluid bed reforming to the levels recorded in the period of the first floating bed operation. This indicates that the floating bed operation is certainly effective for improving the catalyst performance of the catalyst in carbon dioxide reforming of methane. The higher hydrogen and the carbon monoxide ratio in the floating bed reforming could be attributed to relatively less selective towards the RWGS reaction in this type of reactor operation. As listed in Table 1, for the multi-mode switching reforming experiment, the catalyst bed temperatures in the floating bed reforming were always slightly lower than those measured in the fixed bed reforming, but no significant temperature distribution in the catalyst bed was observed. This observation suggests that the improvement of the catalyst reforming performance observed in the floating bed operation cannot be simply attributed to the effect of the bed temperature, but other factors should be taken into account, such as the carbon deposition, radiation extent, and the magnitude of active metallic surface of the catalyst. All of these are what we will do next. And this is the following work. We can do the carbon deposition on the suspended catalyst, the reeducation of the catalyst in the fixed or floating bed multi-mode switching reforming, and the evaluation of the active metallic surface of the catalyst in the fixed or floating bed multi-mode switching reforming. This is the content of my report. Thanks very much.
Okay, thank you very much for your presentation. Okay, now we have finished the session 4 already. Thank you for everyone for your attention. We will come back again at 5 p.m. Now, please take a rest and come back at 5 p.m. Thank you.
It's been 24 hours, I need more hours with you. You spent the weekend getting even, oh. We spent the late nights making things right between us. But now it's all good, babe. Roll that backward, babe, and pay me close. 'Cause girls like you run around with guys like me till sundown. When I come through, I need a girl like you, yeah, yeah. Girls like you love running at me too. I want when I come through, I need a girl like you, yeah, yeah. Yeah, yeah, yeah. Yeah, yeah, yeah. I need a girl like you, yeah, yeah. Yeah, yeah, yeah. Yeah, yeah, yeah. I need a girl like you. I spent last night on the last flight to you. We took a whole day up, trying to get way up, ooh. We spent the daylight trying to make things right between us. And now it's all good, babe. Roll that backward, babe. Pay me close. Yeah, 'cause girls like you run around with guys like me till sundown. When I come through, I need a girl like you, yeah, yeah. Girls like you love running at me too. What I want when I come through, I need a girl like you, yeah, yeah. Yeah, yeah, yeah. Yeah, yeah, yeah. I need a girl like you, yeah, yeah. Yeah, yeah, yeah. Yeah, yeah, yeah. I need a girl 6:45, and maybe I'm barely alive, and maybe this is really it for the last time. And maybe I know that I'm drunk, and maybe I know you're the one, and maybe I'm thinking it's better if you drive. Oh, 'cause girls like you run around with guys like me till sundown. When I come through, I need a girl like you, yeah, yeah. Girls like you look funny, yeah, need to what I want. When I come through, I need a girl like you, yeah, yeah. Yeah, 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 yeah. I need a girl like you, yeah, yeah. Yeah, 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 yeah. I need a girl like you, yeah, yeah.
I won't lie to you, but I know he's just not right for you. And you could tell me if I'm off, but I see it on your face when you say that he's the one that you want. And you're spending all your time in this wrong situation, and anytime you want it to stop, I know I can treat you better than he can. And any girl like you deserves a gentleman. Tell me, why are we wasting time on I always sit around when you should be with me instead? I know I can treat you better than he can. I'll stop time for you the second you say you'd like me to. I just wanna give you the loving that you're missing, baby, just to wake up with you. Could be everything I need, and this could be so different. Tell me what you want to do. I know I can treat you better than he can. And any girl like you deserves a gentleman. Tell me, why are we wasting time on I always sit around when you should be with me instead? I know I can treat you better than he can. Better than he can. Give me a sign, take my hand, we'll be fine. Promise I won't let you down. Just know that you don't have to do this alone. Promise I'll never let you down. 'Cause I know I can treat you better than he can. And any girl like you deserves a gentleman. Tell me, why are we wasting time on I always sit around when you should be with me instead? I know I can treat you better than he can. Better than he can. Better than he can.
There goes my heart beating, 'cause you are the reason I'm losing sleep. Please come back now. There goes my mind racing, and you are the reason that I'm still breathing. I'm hopeless now. I'd climb every mountain, swim every ocean, just to be with fix what I broke, yeah. There go my hands shaking. You are the reason my heart keeps bleeding. I need you now. If I could turn back the clock, I'd make sure the light defeated the dark. I'd spend every hour of every day keeping you safe. I climb every mountain, swim every ocean, just to be with you, fix what I broke, yeah, no, 'cause I need you to see. You are the reason I'm in the corner, watching you kiss her. Oh, I'm right over here. Why can't you see me? No. And I'm giving it my all, but I'm not the guy you're taking home. Oh, I keep dancing on my own. But I climb every mountain and swim every ocean, just to be with you and fix what I've broken. Oh, 'cause I need you to see that you are the reason. I found a love for me. Well, darling, just dive right in and follow my lead. Well, I found a girl, beautiful and sweet. Well, I never knew you were the someone waiting for me. 'Cause we were just kids when we fell in love, not knowing what it was. I will not give you up this time. Darling, just kiss me slow. Your heart is all I own, and in your eyes you're holding mine. Baby, I'm dancing in the dark with you between my arms, barefoot on the grass, listening to our favorite song. When you said you looked a mess, I whispered underneath my breath, but you heard it. Darling, you look perfect tonight. Well, I found a woman stronger than anyone I know. She shares my dreams. I hope that someday I'll share her home. I found a lover to carry more than just my secrets, to carry love, to carry children of our own. We are still kids and we're so in love, fighting against all odds. I know we'll be alright this time. Darling, just hold my hand, be my girl, I'll be your man. I see my future in
Hello.
Hello. Can you listen to me?
Yes, but the next session will start from Xiao Lui Huang from Shenyang University of Chemical Technology.
No, it's my turn, but my name is Zhang Zheng. I'm come from Taiyuan University of Technology.
Yes, it's not your name in oh, okay, you are the last one, right? Okay,
Yes.
you are the last one. Okay.
Oh.
Okay. It's okay. Your PowerPoint is okay. Please show your slide for check. It's okay.
Hello, hello.
Yes.
Is it okay?
Sorry. It's okay.
Is it okay? It's my turn.
So no, the session will start on 5
Yeah,
p.m.
okay.
in Thailand.
Okay.
Okay. Wait,
Only
give us a moment.
10 minutes less. Only 10 minutes.
Yeah,
Okay,
10
okay.
minutes. Okay.
Okay.
Darling, just kiss me slow. Your heart is all I own, and in your eyes you're holding mine. Baby, I'm dancing in the dark with you between my arms, barefoot on the grass, listening to our favorite song. When you said you looked a mess, I whispered underneath my breath, but you heard it. Darling, you look perfect tonight. Well, I found a woman stronger than anyone I know. She shares my dreams. I hope that someday I'll share her home. I found a lover to carry more than just my secrets, to carry love, to carry children of our own. We are still kids and we're so in love, fighting against all odds. I know we'll be alright this time. Darling, just hold my hand, be my girl, I'll be your man. I see my future in your eyes. Baby, I'm dancing in the dark with you between my arms, barefoot on the grass, listening to our favorite song. When I saw you in that dress, looking so beautiful, I don't deserve this. Darling, you look perfect tonight. Baby, I'm dancing in the dark with you between my arms, barefoot on the grass, listening to our favorite song. I have faith in what I see. Now I know I have met an angel in person. She looks perfect, though I don't deserve this. You look perfect tonight. You and me, we made a vow, for better or for worse. universe. I can't believe you let me down, but the proof's in the way it hurts. For months on end I've had my doubts, drying every tear. I wish this would be over now, but I know that I still need you here. You say I'm crazy, 'cause you don't think I know what you've done. But when you call me baby, I know I'm not the only one. You've been so unavailable. Now sadly世界上有很多的东西，生不带来，死不带去。你能带走的只有自己和自己的脾气。你曾拥有最美的爱情，你听过最美的旋律，触摸过一个人孤独的恐惧，也看到过最美的风景。我跌跌撞撞奔向你，你也不能一个人离去。我们在一起说过，无论如何一起经历了风雨，平平淡淡，安安静静的老去。
Okay. Good evening, everyone. Welcome back to YSCRC 2021. This is session number 5. My name is Chanatip Sama from Thammasat University. I'm a chair of this session, and also Associate Professor Suwadi Kong Palakun. She will be a co-chair of this session. In this session, we have 6 speakers. It will be start from Mr. Xiao Lui Huang from Shenyang University of Chemical Technology. He will present in the title of Evaluation of Metallic Magnesium Production from Low-rank Magnesite. Please.
Okay, hello everyone. Can you see my slide?
Yes. Good
Yes.
slides. Okay. Please start.
Thanks for Simon's chairman's introduction. I'm Xiaorui Huang, a PhD student of Professor Xu from Shenyang University of Chemical Technology. The title of my presentation is Evaluation of Metallic Magnesium Production from Low-rank Magnesite. There are 4 parts in this presentation. As the lightest metallic structure material, magnesium has a density of 1.74 gram per cubic centimeter, which is 64 of that of aluminum and 22% of that of iron. Due to the advantage of lightweight, good corrosion resistance, it's widely used such as in automotive, military, 3C electronics, medical, aerospace, rail processing, and others. In 1950s to 1990s, China's magnesium mining comes from Liaoning, and it depends on the electrolysis of magnesium chloride. The high-grade magnesite was used as the feedstock, but this process is high energy consumption and strict material requirements. Moreover, the most greatest disadvantage is the too expensive production cost because of its huge electricity consumption. More consumption. At present, all magnesium is produced by pigeon process because of the low production cost, and the Liaoning's magnesium industry was replaced by Shanxi, and other provinces. Now in Liaoning, the magnesite ores were used as the raw materials for the refractories. According to the calcination temperature, there are many three kinds of products: caustic calcite magnesia (CCM), dead bearing magnesia (DBM), and fused magnesium (FM). Due to the marine strategy of take the rich and discard the poor, a large number of abundant low-rank magnesite is produced, accompanying with the production of magnesia. It's noticed that the content of magnesium oxide is relatively high, and the abundant ores were freed. So, if it is possible to utilize the low-rank magnesite to realize the high-value utilization of solid waste resource, therefore, we propose a new idea for magnesium production based on the low-rank magnesite. In the process, we use the low-grade magnesite to replace the dolomite and use transport bed flash calcination to reduce the energy consumption of the calcination stage by the decreased temperature. From the thermodynamic calculations, this process was proved. But how about the economic feasibility and the industrial prospect? This is the most important factor to determine the application of the new process. In this study, we evaluate the new process by the life cycle and the economic analysis. We modeling LCA of Pigeon Road in Fugu, Shanxi, from grid to gate, coal mining and processing, transportation, chemical, coal gas production, dolomite mining, ferrosilicon production, fluoride production, magnesium production, electrolysis productions are included, and then the model then the model of the potassium rotors was established, and based the model of the pigeon process. The total was calculated by enterprise and calculated by the mass energy balance according to the thermodynamic software. We evaluated the environmental performance and the economic performance. And the environmental performance was evaluated by the impact of PED, that is primary energy demand, and the GWP, that is global warming potential, while the economic performance was evaluated by the production cost, included the cost of the raw materials, fuel, power, and the carbon tax. And by the results of the evaluation, it's possible to determine which route is economic feasibility. According to the life cycle of metallic magnesium from the pigeon process and the mass and the energy flow of pigeon process, we established 6 models in total. The difference in the magnesium production process is mainly in magnesium ingot production as shown in this figure. The provenance process in Fugu was considered as S1. In S2, it's the same as the S1, but the transport fluidized bed is introduced to calcium dolomite. In S3, this process uses limestone and magnesite ores as the raw materials. The antimony was used as the reductant, and the producer gas is used as the fuel gas. In S4, it's the same as the scenario 3, except the coke-oven gas is utilized as the fuel. And for S5 and S6, they are the same as the S3 and S4, except the reductant was replaced as the ferrosilicon. The foreground total of the raw materials and energy consumption in the scenarios are calculated by principles of mass conservation and energy conservation using the relevant data from published studies, patents, and comparisons with the silicon thermal process. Detailed data is given in the previous slide and this table. The background data is retrieved from the China Life Cycle Database, CLCD, incorporated in imbalance software. The total production cost includes the cost of the raw ore, the catalyst, the fuel, the reductant, the power, and the loss reduction cost as shown in this table. Moreover, based on the trading data of the carbon market, the cost of GHG emissions is averaged as 53 yuan per ton. The calculated results of PED and the GHG emissions of S1 are as shown in this figure. For indirect GHG emissions, the ferrosilicons contribute a lot than the semi-coke gas, and for direct GHG emissions, the fuel combustion is greater than the dolomite decomposition. Ferrosilicon, the semi-coke gas, and the washed coal are the main contributors to the PED, and the contribution of dolomite, fluoride, and the transportation could be ignored because of the tiny shares. The PED and the GHG emissions results of the 6 scenarios are calculated and shown in this figure. For GHG emissions, the order is S1 is greater than S5, greater than S3, and greater than S2, and greater than S6, and greater than S4. For energy consumption, the order is S1 is greater than S2, and greater than S5, and greater than S6, and greater than S3, and greater than S4. The energy consumption and the GHG emissions of the 6 scenarios are mainly due to the fuel, reductant, and electricity. For GHG emissions, the relative impact of the 6 scenarios is 186, 87, 70, 99, and 72% respectively. And the relative impact of PED in the 6 scenarios is 118, 7, 56, 54, 62, and 59%. The production costs of the 6 scenarios are shown in figure. In the figure, each bar represents the average value. The arrow line on each bar means the highest and the lowest values of magnesium cost according to a quarter price fluctuation of corresponding raw materials and energy. It can be shown that S6 has an economic performance that is 10% lower than the PGM process. The influence of the variation in key parameters on the production cost of the 6 scenarios are carried out as shown as this sensitivity analysis. It's showing that the reductant price has the largest impact on the total cost. Although the production cost was decreased by the increased carbon tax, the impact of carbon tax on production cost is relatively small. And from our results, we can give this is conclusions. In the production of manganese ingots, more than 19% of the GHG emissions and energy consumption are due mainly to the process associated with fuel production, combustion, and reduction. The GHG emission and the PED in the current PGM process in Fugu are about 39 tons CO2 equal and 630 and 38,000 megajoule, which is calculated by the actual domestic technology level and the upstream product data. And the route S6, which using the reductant coke oven gas from the steel works as fuel and integrating the high efficient transport bed crush calcination of manganese was seen as a feasibility route consider both economic and environmental performance. And this is what I did. And thanks for your attention.
Thank you, Ran, for your nice presentation. So, okay, now it's time up. So if any question from participant, please leave the message in the chat box. The presenter will give your answer. Sorry for very short time. Okay, so we are going to the next speaker. Also from Shenyang University of Chemical Technology, Ping An, right? Okay, so yes, okay, she will present in the topic of optimization of energy efficiency for flash calcination of magnesite in transport bed. Please, Miss Ping An. Yes, okay.
Yeah, can you hear me?
Yes.
Can you see my screen?
Yes, very nice.
Okay. Good afternoon, everyone. My name is An Ting. The title of my presentation is Optimization of Energy Efficiency for Flash Calcination of Magnesite in a Transport Bed. The contents of my presentation include the introduction, objective and method, results and discussion, conclusion. Let's come to the first part, introduction. Magnesia, also known as magnesium oxide, usually comes from the magnesite, dolomite, seawater, and brine. Due to its favorable properties, such as high resistance to fire, high thermal conductivity, electrical resistance, magnesia has been widely used in many fields of refractory materials, construction materials, chemical industry, fertilizers, medicine, magnesium metal and alloys. Magnesia is mainly produced from the magnesite. Magnesite mainly composed of MgCO3, which is one of the most important raw material source for magnesia refractory production. China is rich in magnesite, and about 90% is distributed in Liaoning province, where is the world's largest production and exploitation site of magnesium-based materials. Magnesia is generally divided into three categories: the caustic calcined MgO, CCM, dead burned MgO, and fused MgO. The light calcination of magnesite is the most common method to produce CCM. In the traditional CCM production process, the reverberatory furnace, RF, has been widely adopted for decades. It's a fixed bed calciner. This calciner has the characteristics of high energy consumption, poor feedstock adaptability only for large particles, difficult to control product quality, and serious environmental pollution. The magnesite flash calciner actually is a suspension furnace. It can produce with the poor product quality. Thus, urgent need of upgrading for CCM production technology. Shenyang University of Chemical Technology proposed a transport bed flash calcination TBFC process for the CCM production. In the TBFC process, a transport bed calciner is employed to substitute the traditional RF. In the TBFC process, it can adopt small manganese powder and with high production efficiency, good product stability, and high product activity. Let's come to the objective and the method part. The TBFC process is investigated through process simulation, considering the pre-decomposition of manganese during preheating, aiming at optimizing the energy saving strategy for the process. This figure shows a schematic diagram of TBFC process. The TBFC process is mainly composed of a calciner, implementing the light calcination of manganese, a manganese preheating system, which is heated by the flue gas, and a CCM cooling system, cooled by the air. And a staged combustion is employed to better maintain the temperature distribution along the calciner. This table presents the compositions of manganese and the flue gas. For the TBFC process with multi-stage preheating, the temperature of fed manganese would surely increase continuously. Thus, the manganese may start to decompose even at 500 degrees C. Thus, the pre-decomposition needs to be considered for an accurate process analysis, which in turn requires an input of kinetic data. The kinetic data obtained by manganese calcination using MFBRA was adopted for the simulation. This table presents the representative unit and the corresponding models used in the simulation. The Aspen Plus flowcharts of TBFC, RF, and MFC. In comparison with TBFC, the RF without staged combustion and the CCM cooling, MFC with 2 stages preheating and 1 stage cooling, while also without staged combustion. Considering the industrial application, the energy efficiency of the whole system becomes critical. Thus, this energy efficiency was calculated in this work to well illustrate the superiority of TBFC over MFC and RF. The energy allocation analysis was also performed and discussed. We come to the results and the discussion part. This slide shows the results of energy consumption and efficiency. It can be seen that increasing preheating and the cooling stages reduces the consumption of energy and also raises the energy efficiency. It can be seen that the preheating stages have a bigger effect in the raise of energy efficiency than the cooling stages. Considering the available energy efficiency rise, the industrial application prefers 4 stages of preheating and 2 stages of cooling. This slide shows the pre-decomposition of in preheating. It can be seen that the maximum conversion of pre-decomposition is about 12 to 13% for a 5-stage preheating. Increasing the cooling stages slightly decreases the pre-decomposition of conversion. It can also be seen that the more preheating stages, the higher the temperature of fed manganese. This slide shows the temperature variation in process. From this figure, we can see that raising the preheating and the cooling stages, the flue gas temperature reduces, indicating the higher energy utilization. It should be noted that the temperature of flue gas is already below 100 degrees C after 5-stage preheating. This would be the limit for the industrial application. It can be seen that the number of cooling stages it affects the temperature of final CCM. The energy consumption of TBFC is about 4,100 kg per kilogram CCM, which is much lower than those of MFC and RF. The corresponding energy efficiency is about 66.8%, which is much higher than those of MFC and RF. Well, from the energy allocation, it can be seen that for the RF, there is without CCM cooling. The loss via CCM is much higher than those of MFC and TBFC. For MFC and RF, the losses via flue gas were much higher than those of TBFC. For the TBFC process, due to the staged combustion, it can essentially ensure the lowest amount of flue gas, thus attributes the energy saving also via flue gas. Thus, the TBFC process saves energy by staged combustion and further by the recovery and the reutilization of sensible heat of flue gas and the CCM. And the TBFC demonstration plant is under construction in Liaoning province, China. It's going to be commercial running in this year. The conclusions part. For the TBFC process, increasing the number of preheating stages leads to more pronounced rise in energy efficiency. The preferred arrangement is 4-stage preheating and 2-stage cooling. The pre-decomposition mainly occurs in the first stage preheater. The sensible heat of flue gas is as much as 6 times as that of CCM. The TBFC with staged combustion improves energy efficiency. I would like to thank Professor Xu, Professor Bai, Professor Han, Professor Guan, Professor Abu for their instruction and help. This is all my presentation. Thank you for your attention.
Thank you very much for your nice presentation. It's very interesting talk. Okay, so now it's time up, but I have some short question. If possible, I would like to ask you about your design in the fluid bed, right? Reactor. What is the key design to improve the efficiency compared with the other reactor?
Yeah, I see. Because you know, for the for our calciner, it adopts the transport bed. It's actually kind of a fluidized bed. Well, for the we can see from this in comparison, you know, with the traditional RF and the MFC, we saved energy efficiency. We increased the energy efficiency with what we adopted the staged combustion, and also we further recover the energy by recovery and reutilization of the flue gas and the CCM. So I think maybe we can improve the energy efficiency of the system, maybe including the two aspects. Maybe one is we adopted the staged combustion, and this essentially ensured the lowest amount of flue gas, which you know resulting in the lower energy loss via flue gas.
Thank you. Are there any economic analysis?
Because you know, for this work we only calculate.
Yes. Okay. Okay. Thank you very much. Okay. So yeah. Okay. So we may discuss later. Thank you very much for very interesting presentation. We move to next presenter. Also from Shenyang University of Chemical Technology. Okay. Mr. Sifu Su, right? Okay. He will present in the topic of calcination of small size magnesite in a fixed bed with internal for co-production of high activity magnesium oxide and high concentration CO2. Please.
Can you hear me?
Yes.
Can you hear me? Can you hear me?
Yes, I can hear you now.
Okay, thank you.
Okay, please start your presentation.
Okay. Good evening, everyone. My name is Zifu Xu. I come from Shenyang University of Chemical Technology. The topic of my report is calcination of small-size magnesite in a fixed bed with internals for co-production of high-activity magnesium oxide and high-concentration carbon dioxide. My report is mainly divided into 4 parts. The first one is about the research background. Magnesite is a carbonate mineral of magnesium with the molecular formula of magnesium carbonate. The actual ore also contains a small amount of calcium oxide and silicon dioxide and other substances. China is rich in magnesite resources, and the mining areas are mainly distributed in 9 provinces, of which Liaoning is the most abundant in magnesite reserves. Liaoning magnesite has rich reserves and high quality. However, there are many crustal ores and great losses in mining, and the high quality ores are reduced year by year. The next one is calcination of magnesite is the most effective method for producing magnesite oxide. The reaction principle is that the magnesite carbonate is decomposed by heating to produce magnesium oxide and carbon dioxide. Calcination at 700 to 1000 degrees centigrade is called light burning. Carbon dioxide cannot escape completely. Light burned manganese with strong chemical activity and high viscosity was obtained. The magnesium oxide is widely used in mining fields, in chemical industry, in building materials industry, in paper industry, in food processing industry, and it can be used in agriculture. Carbon dioxide is also a high-quality raw material with applications in many fields. It can be used as agricultural fertilizer, and it can be used as oil displacement agent. It can be used in medical assistance and chemical synthesis and other fields. At present, the calcination of magnesite mainly includes the following divers. The most common industrial divers are laboratory furnace and safety kiln. From the summary, it can be found that the main problem of magnesite calcination are as follows. The first one is the hot flue gas is actually heated to make the carbon dioxide contain a large amount of flue gas and a small amount of impurities. Carbon dioxide, the separation is very difficult, resulting in a large amount of carbon emission and environmental pollution after emission. The second is most divers, like safety kiln, they are difficult to achieve calcination of small particles, resulting in the waste of our resources. The third is the outer heat rotary kiln. It can improve the purity of gas product and calcination small particles, but there is a problem of his power consumption, and its service is difficult to enlarge. Therefore, in this study, the internal was installed in the center of the externally heated moving bed reactor as the gas product channel to change the flow direction of gas product and reduce the thickness of material layer to realize calcining of small particles. active magnesium oxide and high purity carbon dioxide gas was finally obtained. The picture like this is the pilot plant we have built, and the preliminary commissioning has been completed. And the main research contents of this report is take the fixed bed reactor as the experimental device and explore the effect of the internals and calcination of small particle magnesite. The third section is about research results and destruction. 0 to 6 millimeter magnesite were used as a raw material in the experiment. Through the TG-DTA curve, it can be seen that there are two states corresponding to magnesium carbonate and calcium carbonate respectively. When heated to 800 degrees centigrade, the reaction can be considered to have been completed. The content of magnesium carbonate and calcium magnate were calculated in this state is 91.30% and 5.01%. And the experimental conditions are shown in the table. The furnace temperature is 900 degrees centigrade. For the temperature running curve, there are two stages in the heating progress. The first one is 0 to 600 degree centigrade, and the second is 600 to 900. And the time to reach 800 degrees centigrade in the center of the reactor A is relatively short. The heating rate of reactor A with internal is bigger than that without one. I'm sorry. The internal enhances the heat transfer of the inner layer. For the particle size, the average particle size of magnesite also is as follows. After calcination, the total mass after burning without internal is slightly higher, and the particle of 0 to 1 millimeters particles of without internal is lower than that with internal. The content of 0 to 1 millimeter particles increase while the content of other particle size decrease. It promotes that the internal promote the decomposition and the fragmentation of magnesite. For the gas generation rate, there are two stages. The first stage is 0 to 55 minutes, and the second is 55 minutes to the end. At the 55 minutes, the reaction rate reaches the maximum. In this time, the gas generation rate of A is faster than B. In the total time for completion of gas generation is A less than B. The gas generation rate is A greater than B. This promotes that internals are conductive to improve heat transfer rate and light burning reaction rate. And the carbon dioxide concentration, you can see the picture, they are quickly reached by 98%. When the gas generation rate about 0.5 liter per minute and the reaction time of A and B are 150 and 237 minutes respectively. After that, the carbon dioxide concentration decreased significantly, less than 90%. This work in concert with the gas generation curve. For the conversion rate, the conversion was calculated by carbon dioxide concentration. The concentration rate increased gradually with the extension of time. When the temperature reaches about 800 degrees centigrade in the center, the conversion rate tends to be stable, and the time span is the without one is bigger than the with one. This proves that the internals promote the calcination of magnesite. For the ignition loss rate of product.
To me, please summarize your talk. Now it's time up. Please, please conclude your talk.
Okay. Okay. The conclusion. The use of the internals in the bed can improve the heating rate of magnesite particles to more or less reduce the time taken for increasing the central temperature of the particle bed to 800 degrees centigrade. The content of active magnesium oxide in the calcinated product from the reactor with internals reached 81.99%. This is indicated that the internals can get the high temperature gas flow from the generation point to the low temperature collector along the radial direction, thus enhancing heating transfer to particles in the reactor and in turn reducing the time required for complete reaction. Under all conditions, the carbon dioxide concentration in the effluent gas of the reactor is more than 98%. Consequently, the reactor with internal can be well used to calcinate small size magnesite to co-production high activity magnesium oxide and high concentration carbon dioxide. That is content of my report. Thank you, everyone.
Thank you very much for your presentation. Okay, now is a time up. We going to the next presenter. Please, Dr. Suwadi, to introduce another one.
Okay, for the next presenter from China University of Mining and Technology, Xiaorong Wan, would you please share your slide? Are you there? Okay. Yes, could you show full screen?
Can everyone hear me?
Yes, clearly. Okay, you can present now. You have 10 minutes for presentation, please.
Oh, thank you. Good evening, everyone. My title about my representation is the effect of temperature and atmospheres on ash-century characteristics of fossil residue with high potassium and sulfur. My report will contain these 4 parts. First is the research background. Second is the experimental materials and methods. Third is the results. And 4 is the conclusions. First, I would like to introduce the research background for all of you. At present, the main treatment method of fossil residue are accumulation and landfill, which waste resource and cause environmental problems. The energy-based utilization of combustion has the advantages of large processing capacity and higher conversion efficiency. However, fossil residue is rich in alkali and sulfur, which is easy to affect the operation of the device due to ash-century and corrosion. Therefore, it's necessary to study the migration of potassium and sulfur elements and the century characteristics of ash from fossil residue. Now we may move to the experiment parts. The material we use is the fossil residue from a fossil production enterprise in Liaoning province. The property of it shows in table 1. We can see clearly that the fossil residue has large amount of carbon and oxygen. And the ash sample was prepared in one pure furnace at 550 degrees for 90 minutes. The XRF analysis of it is shown in table 2. We can see the content of potassium and sulfur oxides are obviously high. Now, this figure 1 shows the schematic diagram of the experimental system for ash agglomeration. We can use it to get the ash morphology of it. The shrinkage degree of ash was measured by the volume change before and after heated. The potassium and sulfur content of ash was determined by XRF, and the mineral species were determined by XRD. The macromorphology was observed by SEM. Here's the results. From the pictures, we can see clearly that after heated, the ash morphology changed a lot. The color from the original into red, and the shrinkage rate is high. With the increase of temperature, the shrinking rates increase in all atmospheres with different degrees. In pure atmospheres, the central temperatures are 1,100, 1,150, and 1,150 in nitrogen, carbon dioxide, and oxygen. In mixed atmospheres, the central temperatures are 1,000, 1,100, 1,100 degrees, desperately in nitrogen and steam. Carbon dioxide mixes the steam and oxygen mixes the steam. It shows that the steam promotes the shrinkage of ash samples and decreases the central temperatures. Here is a macromorphology of ash samples at different temperatures in nitrogen and nitrogen mixed with steam. The figure 7 shows the macromorphology of ash in carbon dioxide and carbon dioxide mixed steam. And the last one shows the ash morphology in oxygen and oxygen with steam. This picture shows that before the obvious centering of the ash, the melting phenomenon has appeared in the microstructure. Compared to pure atmospheres, steam introducing promotes melting. SEM analysis showed that the temperature of agglomeration and centering in mixed atmospheres decreased significantly. Here shows the XRD results of ash samples in nitrogen and nitrogen with steam. The next one shows the results in carbon dioxide and carbon dioxide with steam. The last one shows that in pure oxygen and oxygen with steam. Here's the results. The table 3 shows the composition of ash. The table 4 shows the reaction occurred at high temperatures. According to the table 3, it is found that the main components of ash are quartz, microcline, and andesite. According to table 4, in pure atmospheres, it indicates that nitrogen promotes the decomposition of microcline. Carbon dioxide decreases the temperature of microcline forming to inhibit the decomposition and prevents the centering of ash. High content of potassium is easy to form low melting point potassium aluminosilicate and form low temperature autotech. After the introduction of steam, the kinds of potassium aluminosilicates increase the promotes the fusion. Here shows the migration of potassium and sulfur in ash. The retention rate of potassium gradually decreases with the increase of temperature, and at the 1000 degree, the retention of potassium is highest in carbon dioxide, the smallest in nitrogen, because the ash are centered in nitrogen and the microcline decomposed, then a large amount of potassium escapes. The retention rate of sulfur decreases with the increase of temperature, especially when the temperature is higher than 900. At isothermal temperatures, atmosphere has little effect on the retention of sulfur. As can be seen from the figure A, the retention of potassium decreases with the increase of the temperature, and the difference is not obvious at high temperature. And in figure B, we can see the retention of sulfur decreases significantly with the increase of temperature. And compared with the pure atmospheres, the influence of atmospheres enhanced after the introduction of steam. Here's the conclusion. In poor atmospheres, the shrinkage rate of ash increases with the increase of temperature. The mixed steam atmospheres promotes centering, and with the increase of temperature, the retention rate of potassium and sulfur in ash decreases. Mixed steam inhibits potassium escapes at low temperatures and promotes the sulfur escapes. And carbon, we can use atmospheres includes oxygens and carbon dioxide to inhibit the centering of ash. And if we need to burn the fossil residue, we should to control the temperature below 900 degrees. Thanks for listening.
Okay, thank you very much for your nice presentation. We still have time for one short question. Are there any questions? Maybe I check in the chat box first.
I have a question.
Yes, please.
Yeah, in your study, you investigated the temperature and the atmosphere effect on ash sintering. So, in your opinion, the temperature and the atmosphere, which you think is more obvious of a factor, the ash sintering, which is play the controlling role?
I think is the temperatures. The atmospheres only affect the temperatures at a temperature space such as about 100 degrees. Maybe infect it to get lower or higher.
Okay, I see. Thank you for your answer. Thank you.
Thank you.
Okay, thank you very much. It's about the time for the next speaker. Thank you. Our next speaker, Ms. Tranti Thongvi from Nguyen That Thanh University. Okay, Dr. Vivi, could you share your slide, please? Okay. Yes. You can show full screen. Okay. Okay, full screen now. Okay, good. Okay, let's start.
Okay, so thank you very much for your interview for me. So my name is Tranti Thongvi. I'm from Nguyen That Thanh University, and today I would like to share with you about my research work in the topic preparation of silver nanoware decorated recycled secrets filter based on composite with highly efficient EMI shielding. And what is the image shielding? So let's start with the introduction. So as we know that nowadays the interest about the increasing of the industrial and also the electronic device. So we will focus on the development of the smart and intelligent electronic device. So we will call it 5G or fifth generation. And so many problems come up with the development of the electronic device and industrial development during the effect of the signal on the human health, and also the increasing the temperature of the device, and we make the reduce the time of the electronic and also the device. So that's why the scientists and the researcher that will find the new material that have could be solve the problem and can be prevent and protect the human health, and also protect the electronic device. We will call that EMI shielding. And EMI shielding is one of material could be protect the signal and also prevent the generated signal from the electronic to the pupil and to the environment. And at the previous work, they also study with the copper, silver, and another metal. Due to the high thermal conductivity and also high shielding efficiency, however, there still remain some disadvantages such as density, high density, and high cost also. So that's why in our research that we try to focus and reduce the weight from the secret filter of CF. And this CF that also that have suitable property that have the consist of the framework related with the vertical aligned cellulose microfiber, and this one also the same direction with the heat transfer. And after we using this material, so it could be decreasing the cost of the material and environmental pollution control. Why we call that environmental pollution control? Because as we know that the secret filter that can consist of high cellulose acid, and this one of the main component is non-degradable. And after we reuse that one, it could be reduce the environmental pollution. And also we also start using the silver nanowire due to the high thermal conductivity, and also when we compare with the another metal such as copper nanowire or nickel, so it could be reduce the oxidation in the air, and could be take the long term of the equipment or the device. And let's move to the preparation of the material. So first of all, we will prepare the material from the silver nanowire attached with the CF, or we call that either secret filter. This one after we collect, so we will remove the image by using the solvent ethanol. And after that, we will pre-treating and then drying at 60 degrees C for overnight. And after that, we will got the cellulose skeleton. And we're using this material for immerse in the solvent that contain of the silver nanowire substance. And this one is commercial one, and we post in the industry. And after finish, we coating for 2 minutes. So we will pick it up and then dry it. And this step will repeat at 10 times. And after finish, so we also continue the next step that also immerse in the epoxy composite to make the foam. And after finish, we also study and dry it at 60 degrees C for 2 hours to remove the bubble in the vacuum oven. And after finish, so we also analyze it with many techniques to study the foam morphology, the thermal conductivity, and also EMI shielding performance. So with the morphology structure, so we can see that in the slide, start from figure 8, maybe it's too small, start from figure A to figure G. So this one is same image of different deep coating cycle. So the first figure is the 1 cycle and follow up in up to 10 cycle. And we can see that the surface of micro fiber become looser due to the presence of the silver nanowire on the surface of the material. And after 10 cycles, so we can see that totally fully of the silver nanowire will attack on the surface of the microfiber. So that's why we will stop at 10 cycle. Because as we know that silver nanowire also one of solution is quite high cost or costly. So we try to minimize the amount of the silver nanowire using on the material. And the last figure is so the EDX image, and it could confirm the silver elemental. And for the next result, that we also study the thermal conductivity of the LC composite. So we can see in here that we will start with 0% of the silver nanowares. So it means that this one is the build of the LC, and we can see that the thermal conductivity is quite low, only 0.2. And after we increasing up to 10 cycle, it means allow 2.8% volume of the silver nanoware. So the thermal conductivity, it will increase to 1.7. So it means that it will increase around 700 times. And we also study with two directions. So we can see we start with the throw plane with the red color, and also in plane. It means that we will start from measurement the parallel direction, and we can confirm that the heat transfer will affect on the throw plane, and it could be follow the direction of vertical. And beside that, we also compare our work with another material fiber and another work that they're using another different kind of material. Our work didn't show the high heat result. However, it still present the good thermal conductivity when we compare with another work. And the next result, that is the thermal minimum capacity of the epoxy composite. So with the figure A and figure B, it during the heating time, and figure C and figure D, it during the cooling time. And in the left hand side, this is the PLC. We would like to compare with 3 different samples, and the middle is the random of the deep coating cycle, and the last one is the good condition of the after we deep coating 10 cycle of the silver nanoware. So we can see that with the heating time, it's very quick, only after 10 seconds. So the material is quickly to heating up to maybe nearly 40 and 50 degrees C, and also the same with cooling time. So after 10 seconds, so the temperature reduce very fast. So it could indicate that the quick thermal response to the silver nanoware and the sample when we compare with the other sample. And in this slide, that we also present the image shielding performance. And in this slide, that we study about the electrical conductivity when we increasing the percent weight of the percent volume of the silver nanoware. So the electrical conductivity also increasing. And in the figure B, that we will study with different deep coating cycle, and the total image shielding also affect and increasing up to 40 decibel. And for conclusion of this work, so I will explain a bit about how image shielding working. So we can see in the figure A in the left hand side. So this one is my material, it's our sample. And at the time when the external waste, so we call that EM waste attack or expose on the material. So a part of the wave will reflect it. Due to the sample that have too many layers of the cellulose microfiber, so it will some part will reflect it, and another the part remain will be absorbed on the material. So that's why it could be reduce the waste when the external waste exposed on the sample. And the figure B, that we also compare our work with another work in the reference, and we can see that our work did not show the high performance. However, it also provide a reduced environment and also transfer from the waste to the useful product. And for acknowledgement, so I would like to thank Petrochemistry Group, Thammasat University, and also Faculty of Environmental and Food Engineering with Winterthur University. And thank you very much for your kind attention.
Okay, thank you very much for your nice presentation and share us about the idea to recycle the cigarette for much more useful. There is one the question from the chat box. Okay, what is the performance of the material after more than 10 cycle of dip coating? Is there a limited cycle number?
Yes, thank you very much for the question. So we not have the limit of the cycle, and we will know that after we increasing more the cycle of dip coating, it will increasing the performance. However, because as I mentioned before, the silver nanowire is quite expensive, so we try to minimize the amount of the silver nanowire attack on the secret filter. So if we can see that it fully attack on the surface, so we will stop the cycle. If we try to increasing it, that is okay also. It not have any limited about the cycle of dip coating.
And are there any leaching along usage? I mean, like if you apply for the applications, are there any leaching of the coating?
Because after we coating with the silver nanowire, so we have another step that we also coating with the LC. So I think it did not leak.
Yeah. Okay.
Yes.
Thank you very much for your nice presentation.
Yes, thank you very much.
Okay. Next speaker. Okay, our last speaker for today, Cheng Chang from Taiwan University of Technology. Would you please share your slide? Okay, and full screen, please. Okay. Okay. So you can like turn on your microphone. I cannot hear anything for now. Could you check your microphone, please?
Okay.
Okay, it's okay now. Good.
Okay.
Okay, let's start.
Good evening, everyone. My name is Zhang Zheng. I'm from Taiyuan University and of Technology. I'm so glad to have the opportunity to report my research and share something with you. The topic of my report is a scalable porous composite electroactive film for selective recovery of lithium ions. My presentation will be divided into the following three parts. First, research background. Lithium as one of the important energy elements in the 21st century due to the development of the intermittent renewable energies and the widespread use of the portable electrical devices. Lithium is quickly emerging as an important commodity. One can see that lithium batteries have a widespread application in our daily life. Thus, the recovery of lithium resources have drawn on increasing attention in recent years. Lithium resources are mainly distributed in lithium ore, seawater, and salt lake brine, in which the extraction of lithium from brine should have great potential because of the identified lithium reserve account for 66% of total global lithium storage. Lithium resources are widely distributed on Earth, and the Chinese lithium resources are mainly stored in salt lake brine. The conventional technology for lithium recovery from salt lake brine conclude adsorption solvent extraction, and so on. Among them, the adoption method has become the most option due to the high adoption capacity and the target selectivity. However, the adoption method is still a time-consuming process and could generate secondary pollution. Therefore, it's desired to develop more environmentally friendly and effective approach for lithium recovery from brain. YSCRC is an environmentally benign and efficient ion recovery way, which can realize rapid uptake and release of target ion from addressing the redox state of the YSCRC film. For the recovery of lithium, it is of great significance to investigate a suitable lithium exchange material. The magnesium dioxide exhibits outstanding lithium ion selectivities because of its specific imprinted vacant site. However, the magnesium dioxide have poor conductivity and low film ability on the electrode for the YSCRC process. Here, a strategy was designed for the fabrication of scalable porous composite electrode active film. That is a well-dispersed solution, consists of magnesium dioxide, RgO, and alginate. Was freeze-dried to fabricate the composite film, in which the magnesium dioxide nanorods was immobilized on the surface and in the pores of RgO and alginate, and worked as potential responsive lithium ion recognition unit. And meanwhile, the alginate binder played a key role in the formation of the composite film with high stability in aqueous solution. Figure 2 shows the same morphologies of LMO, magnesium oxide and magnesium oxide RgO alginate composite, and the core and the cross section of the composite film with different magnification, and the photograph of the composite film with a large size, with a size of 10.7 cm in diameter. Following are the corresponding characterization of the composite film, and figure 3E shows that there are no redox peaks or observed in CV measurements of sodium and magnesium. In contrast to pairs of redox peaks were cleared observed in CV curves of lithium, proving that the composite film have high selectivity, had high selectivity of lithium ions. Figure 4 shows the YSCRC magnesium of the composite film for the recovery of lithium ions. When a reduction potential is applied and the electrode, the composite film is reduced, so that lithium in the aqueous solution are selectively intercollected in the magnesium dioxide to maintain a charge neutrality. On the contrary, when oxidation potential is applied, the film changes to an oxidation station, so that intercollected lithium are released to the solution. Figure 5A and B shows the adoption capacity of lithium ions on the composite film at different voltage and initial concentration. The adoption capacity of lithium ions gradually increased with the increased voltage and the initial concentration. The selectivity of the composite film for lithium sodium and lithium magnesium separation was evaluated by means of competitive adoption in a mixed solution. The result demonstrated that the obtained film maintained a great selectivity for lithium. Conclusion: the obtained film showed greater ion separation performance and the adoption capacity of lithium ions research up to 32. More than 90% of its adoption capacity was achieved in 1 hour. The composite film displayed excellent selectivity towards lithium ions, and the separation factors for lithium, sodium, and lithium magnesium researched 1040 and 358 respectively. Okay, that's all. Thanks for your listening.
Okay, thank you very much for your presentation. Okay, are there any questions from the participants? We still have time, about 2 minutes for question. So during waiting for the chat box, I have a question. Are there any effect of the manganese oxide, graphene oxide, right, and calcium? The ratio, is it effect to the efficiency? In this work, you prepare composite, right?
Please repeat it.
Okay.
I can't listen.
So in this work, you prepare composite of manganese oxide, graphene oxide, and also calcium with the alginate, right?
Yes.
Is the ratio of this material effect to the efficiency?
Yes, and its adoption adoption capacity of lithium ions reach up to 32.7, and it can achieve in 1 hour. So it is efficient.
Yeah. Okay. So with this for material that you mix together as a composite, which one is the most important for removal of the lithium ion? You have manganese oxide, right? Graphene oxide, calcium, and also alginate. So you have to balance the ratio of this composite, right? To making sure that it can be achieved the lithium ion recovery, something like that, right?
Yes.
Okay. So what's the ratio of this component in the composite? I mean that the ratio that you mix together of manganese oxide, graphene oxide, and also calcium alginate. Or the fraction of this material. Are you okay?
Sorry, please repeat it. I can't listen.
Okay. From this slide, right? That is you mix manganese oxide nanorods, reduce graphene oxide sheet, right? And also calcium alginate. That slide is okay. 12. Slide number 12, please. Okay. So you fix the weight ratio, right, of the composite, and then test for lithium ion removal, right? My question is that how to balance the weight ratio to achieve the selectivity of lithium-ion recovery.
I'm sorry, I don't know.
Okay, that's okay, don't worry. Okay, so it's about the time, and thank you very much for your nice presentation. And before we ending the session tomorrow, I have some announcement for tomorrow. Okay, so tomorrow we will start the session at 13 or 1 p.m. in Thailand time. And Professor Ping Yerding from Wuhan University, he will present about the efficiency of converting syngas to liquid fuels with the reduced carbon dioxide emissions. So everybody, please join us for today, for tomorrow. Okay, so see you tomorrow. Bye bye.
See you tomorrow.
See you tomorrow.
Bye.
Bye-bye.
See you.
See you.
You.
Bye bye, Dan.
Bye bye. Okay, maybe I will leave the audience, leave the room first, and then I will leave at the last. Okay, see you all. And tomorrow we have the best oral presentation announcement also. Okay. I think they still have some participants still in the room. Let me check. Okay, maybe I will leave the room now. See you tomorrow. Bye-bye.